talk about CO2 entropy. So thanks, Tadashi, and I hand it over to you to start that.
Okay, so first I'd like to thank Alpa and Shiboro and Aninda for kind invitation to very interesting workshop. And here I'd like to talk about some new generalization of entanglement entropy, which we call pursued entropy. I will explain a definition of this quantity later, but it has some very simple gravity duals that much like holographic entanglement entropy. So it is from a holographic viewpoint, it's very natural quantity, natural generalization of entanglement entropy. And this work is based on these collaborators, Ari Morabashi, Yoshifumi Nakata, Tatsuma Nishioka, and Yosuke Taki, and Kotaro Tamaoka, and Nishaue. So, okay, let me start. So, yeah, let me start with quantum entanglement. I think many of you are familiar with this. So, this is about the bipartite correlation. So, we consider some two parts, A and B. We separate the total system into two parts, A and B. And the quantum entanglement means these two parts are quantum mechanically correlated. And the most famous example is Bell state, EPR pair, like this. And this is example of maximally entangled state. Right? If one spins up and second spins automatically down, and vice versa. If we measure first spin, then we know second spin, consequence of second spin. And so we say for there are non-zero quantum entanglement, if wave function cannot be factorized into this direct product form. This is about pure state. For pure state, this is a definition of quantum entanglement, and the mixed state is more complicated, but I'm not, in this talk, I'm mainly focusing on pure state, entanglement in pure states and some generalization of this idea. And the best measure of quantum entanglement for pure state is well known. This is the entanglement entropy. And heuristically, entanglement entropy measures the number of EPR pairs, their pairs sit between A and B. We can make this more precise. That's I will explain later. But anyway, so entanglement entropy in our context, like the high energy context, we normally define entanglement entropy like this. This is, I think, many of you are very familiar with this. So we separate Hilbert space into HA times HB. This is direct product. And we talk about reduced density matrix by tracing out some part B. And we just focus on A. Then we lose some information. And then some amount of lost information is measured by von Neumann entropy. This is a kind of information entropy. This is a quantum version of Shannon entropy, information entropy. And there is minus trace log rho. And this is SA. This is about for subsystem A. And this is the definition of entanglement entropy. And if we have lots of spins, we can just geometrically choose subsystem A to be like some region, which you like. And if we take continuum limit, then it's like just specifying some boundary of A. Once you specify boundary of A and B on some time slice, then you have this direct product. And then we get we can define entanglement entropy. So this is usually what we do in high energy physics. But in this talk also, it is quite useful to think about entanglement from original quantum information theoretical language, especially some quantum information textbook like Nielsen and Chan. Then they introduce entanglement entropy in the following way. So we have like pure state, and we separate Hilbert space HA and HB. You can imagine some spin, some part of spin is A, the other part is B. And then we consider two different operations, which we can do it in a laboratory. So this is called LOCC. LO is local operation, and CC. Let's assume two laboratories are very far apart, very far distant from each other. Then we can do some very sophisticated quantum operation inside each laboratory. This is a local operation. So projection measurement, or unitary transformation, and so on. And we can do it. But because A and B are so far apart, we cannot act quantum operation at the same time so that it's A and B are both are changed. So between A and B, we can only do some classical communication, like just calling, telephone, or emails, and so on. Just classical bit 0 and 1, classical bits. We can just exchange classical information. And this is, and combine these two is kind of a realistic, operation which we can do between two distant laboratories. And this is called LOCC. And the basic idea of this LOCC is the entanglement doesn't increase under LOCC. Entanglement is something very important, and it should not increase under LOCC. And the basic example of LOCC is quantum teleportation. I think we are familiar with this. But anyway, by using this LOCC, we can extract we can make precise the meaning of extract entanglement. This is kind of distillation, entanglement distillation. We have some very complicated quantum system. It's not like Bell pairs. It's more complicated. There are multi-partite entanglement here. And they're very complicated, but by acting LOCC, we can extract some number of EPR pairs, Bell pairs. And let's assume if we do some of this LOCC operation, and we get the n Bell pairs, but more precisely, we should take a copy of the original system. Let's take M copy. And then we find n Bell pairs by LOCC. And let's take maximum value of n, right? So we optimize this, protocol, and we get a maximally n Bell pairs like this. And then we take this limit, like m goes to infinity. This is called some asymptotic limit. We make everything is more ideal situation. And if we have just one single, just 2 qubit system, we cannot extract more than 1 qubit, right? And we cannot realize 0.5 like entropy and so on. So we take an infinity many copies. This is the asymptotic limit m goes to infinity, and take ratio n over m. Right? And this ratio has a very nice property. And in the end, there's a very famous theorem. This basic theorem in quantum information tells us this is exactly same as von Neumann entropy, which we defined in this way, just rho log rho. So that way we can, even though we are computing this way, but we can interpret this quantity as a just effective number of EPR pairs between A and B, because we can physically extract some number of EPR pairs, and they coincide. And this is quite a well-known fact. And we, in the end, we want to try to generalize this idea to our pseudo entropy. Okay, so these are just basically textbook thing. But I'm going to also other textbook and holographic basic properties. And so I'd like to explain. So first, I mentioned some holographic calculation of entanglement entropy, or some generalization of that. And here I'd like to talk about version 1 and version 2 and new version 3. This is our basically what we want to talk today. This version 3. But before that, let me just quickly remind the version 1 and version 2, and we use, of course, AdS-CFT. So version 1 is like static space-time. So we call it AdS-CFT and just static space-time. In that case, we have some anti-de Sitter space, and its boundary is conformal field theory. And this is just, we can imagine just, one calorimetric. And then we can calculate entanglement entropy in a dual CFT, which is static state, like ground state, or a final temperature state is static state. Then we can calculate it as a minimal area divided by 4G. So this is a holographic entanglement entropy for static spacetime. Okay, and then I'd like to go to version 2. This is a time-dependent version. This is also, we call it covariant holographic entanglement entropy. This is, we can apply for time-dependent backup. So you have some AdS-CFT, but we can modify CFT state in some excited states. In general, we have a time evolution. And accordingly, AdS spacetime, asymptotically AdS spacetime is also Lorentzian, but also time-dependent. In that case, we pick up some subsystem A, and we calculate the entanglement entropy in the boundary CFT, which is time-dependent. And in AdS side, we can just compute this area, but this area is not the minimum because we are talking about the Lorentzian. This is extremal. We pick up extremal surface. Extremal surface, we extremalize the area function. And if there are several candidates, we have to minimize among some discrete number of such candidates. But anyway, so this is a covariant holographic entanglement. So we have some time-dependent state, and we trace out B. B is a complement of A. And we define time-dependent reduced density matrix, and we calculate rho log rho, right? Entropy. And this is computed by this. This is also well established fact. And today I'd like to go one more further step. Actually, there are, even though maybe you might think this is static and time-dependent, so this is everything, maybe. But actually, we are missing something important, one more. So this is a version 3. So what we would like to consider is time-dependent, but Euclidean time-dependent. Euclidean time-dependent background and consider minimal surface. This is a Euclidean asymptotic AdS. So we can, so minimal surface is very different. We don't need to talk about extremal. We just minimize area. And then this is, anyway, obviously this is a nice quantity. So what does this correspond to, right? In CFT? Naively, you might think some sort of entanglement entropy, but this is not precise actually. So precise statement is as the next one, like this. So this guiding principle is, anyway, we talk about Euclidean path integral. And the good point of Euclidean path integral, we can prepare some state, right? You can imagine Hartree-Hawking like prescription. You can create, for example, ground state by path integral for infinitely long time, right? Everything projected down to ground state. But if you can also insert some operator in the middle and do path integral, right? Euclidean path, then you create some excited state, like here. So path integral, this is a cylinder, like a CFT on cylinder, and inside AdS spacetime appears. But the boundary CFT leaves the boundary. And we path integral up to this tau equals 0, right? And we put some insert 2 operator, then we get some excited state here. But we can insert some 3 operator in the upper part. Then we can imagine some opposite path integral, right? Then we have Bra and Ket. We can path integral from plus infinity to 0. Then again, we create some excited state, but different excited state because now 3 operators there, right? Like this way. So this is so we have a final state. This is, we call it the upper state of the final state. And the first one is the initial state, right? And then initial state and the final states are different. So this is a very important point of this Euclidean path integral. And so two states are different. So anyway, we have to consider some quantity. If we are interested in some minimal surface like this, then this minimal surface area should depend on both of them. So some quantity, this quantity depends on 2 different states. That means we have to go beyond normal entanglement entropy. But again, we can just go back to original, AdS-CFT, and we know how to, consider such a correspondence. We know partition function in gravity is equal to partition function in conformal field theory, Euclidean partition function. So, and like Lukowitz and Madison derivation for graphic entanglement entropy. So we can do the same thing. Then, actually, if you are familiar with it, probably you can quickly find out the correct answer. And the final answer is this quantity. This quantity is much like von Neumann entropy, right? Tau is some as I explained. So this is a kind of which we call transition matrix. But tau log tau, it's much like the von Neumann entropy, but tau is something new. Right? Tau A depends on 2 different states, initial state and final state. And it's anyway, trace out B, so we can call it reduced transition matrix. And this original one is defined by this transition matrix. Right? We have an initial state and a final state, and Brand. Okay, this is no longer Hermitian. This is no longer Hermitian, so this is no longer Hermitian. That means this entropy is not always real values, real and positive, that means it's not standard entropy. So we cannot call this as regular entropy. That's the reason we call it pseudo entropy. So, but this kind of idea, even though this quantity itself, we define this is for the first time in this context, but actually there are some cross-related quantity introduced by quantum information people, or some conditional entropy version of this quantity is already considered here. Okay, and I will give more details later, but before I go, so let me give one more motivation why we consider this quantity. So, so how it is useful. So there are many reasons this is useful, but another viewpoint is like something related to topological order. So this actually clarifies, this maybe give you some heuristic interpretation of this quantity. So idea is like this. So you can imagine just AdS-CFT. So we have some boundary field theory and dual to some bulk space-time. But let's consider some boundary CFTs defined by foreign, not the CFT actually. So this define this. This is actually in some gapped phase. But let's assume some topological phase. One gapped phase and the other gapped phase are topologically distinct, different phases. Right? Like if you know this quantum Fourier effect, then filling fraction is different. And in that case, there are some edge, right? Interface appear. This interface, only on this interface, there are gapless mode, like sometimes free scalar, but in general, it's maybe interacting CFT appears. So here in the bar, in this region, and blue region and green region, they are gapped quantum field theory, but on this edge, on the interface, we have gapless mode. And we know gapless mode is CFT. So if this is relativity, this is CFT, so that it's dual to some AdS, right? AdS space-time. But on the other hand, here, gap to space. Gap to space is dual to AdS soliton, like confining geometry. Right? So it's like very shrinks. It doesn't have an infrared region, but only infrared region appears along this gapless mode. along this interface. So if we calculate entanglement entropy, right? If we just calculate entanglement in topological phase like this way, or this is actually very small in general. Maybe sometimes pick up some topological contribution, but it's very small. But if we calculate just entanglement entropy on this, but this is not exactly entanglement entropy because it's now two states are different. Actually, this is pursued entropy. If you calculate pursued entropy on this interval A, so that it's A precisely sit on this interface, then this minimal surface extends along this area space, which goes to infrared. And this gives a very large value, large area. This gives but it's very much smaller. So that way, this what we wrote in the below delta S, which this is some quantity which we take a difference between basically this quantity and original value, basically. So this is actually becomes positive. But as we will see later in a numerical calculation, this quantity typically, usually this becomes negative, non-positive. So when this becomes positive, then actually we can see this we can expect such a non-trivial scenario. That's the reason this quantity it becomes some interesting order prime. Anyway, I will come back to this more detail. And this is here is the context. I just finished the introduction and give definition of pursued entropy and properties, and explain some little bit about qubit system, so how this quantity behaves, and holographic calculation and free field, free scalar calculations, and its connection to phase transition. And also, if I have time, I also mention topological pursued entropy version of this quantity. Okay. So this is a definition of pursued entropy. Already I gave it, right? This is rho minus tau log tau, but this tau is this transition matrix, right? And we separate the Hilbert space A and B, and we trace out region B. Then we define this quantity. This is a reduced transition matrix, and this is standard Rényi version, Rényi pursued entropy, just Rényi entropy, generalization of Rényi entropy with the index n. Okay, and if we take n equal 1, as usual, this becomes von Neumann-like quantity, and this case just go back to original definition of pursued entropy. Okay, and this guy is not quantum state, as I mentioned. It's not Hermitian, so it's not regular quantum state. It depends on initial state and final state, and that's the reason. So we get this quantity is in general complex valued in general, but in some holography, it's like area, it becomes real, and but it has some reason because it's Euclidean path integral. And if we total system, if B is empty, right? If everything is A, then this projection like property is true, or always true, and we don't need to trace out B. So this is always trace is always 1, and the entropy is just 0. So this is also consistent with. I mean, if we take these two states are the same, then this is just standard entanglement entropy. This is something we know. For pure state and full state has a 0 entropy. Some analog in this case. It's more general because of psi and bar phi. And either bar phi and psi has no entanglement, only one of them, but still it is enough to say this entropy is just 0. Always it's 0. So in that sense, it's somehow it seems this quantity is also related to quantum entanglement. It's more complicated. And if we flip this initial state and final state, we just get a complex conjugate. And so in entanglement entropy, we know famous property like SA equals SB for pure state, and same thing also true in our case. This symmetry. And also, if we set these two guys the same, then we get normal. If we psi and initial state and final state is the same, then of course it gets reduced to standard entanglement. Okay, these are basic properties, but very similar to essentially it's a kind of generalization of what we know about entanglement. And so one comment, this is actually so also in quantum information viewpoint, actually sometimes people consider this kind of asymmetric quantity expectation value, like bar phi and psi are different, initial state and final state. This is a kind of final state projection we are doing. So we can indeed realize such a situation in real experiments. And if we take some Hermitian operator, but if we take this average, this is no longer real value because the initial and final state. But nevertheless, we can this is well known. This quantity is called weak value. This is work out first constructed by these people. And then also some experimental protocol to measure this imaginary part and both real part is actually well is known. So that way, this itself is a kind of physical quantity. And but in our case, what we are doing here, sorry, we are not talking about Hermitian operator. We are talking about entropy. What we call pursued entropy. Actually, in our language of this holographic entanglement entropy, so we know, right? So expectation value of area operator is entanglement entropy, or you can regard area operators as modular Hamiltonian. Expectation value of modular Hamiltonian is entropy. But actually, what we are doing is actually weak value of area operator. This is exactly what we are computing as a holographic entanglement entropy. So this is kind of analogous to this weak value generalization of this quantity. Okay. So now I go to kind of quickly go to general perspective of pursued entropy, but later I just focus on more kind of familiar one. Yes.
That's a quick question. So in the entropy, in the last equation on the slide, wouldn't you replace that with a new sort of modular Hamiltonian? Because it's not the same modular Hamiltonian whose 1-point function you should compute, right?
Good point. Yeah, you are right. So here, it's area operator is area operator in Euclidean geometry. But yeah, this yeah, you're right. Yeah, A is very complicated. Okay. It's not just a log of some density matrix.
Right. Okay, got it.
But so this is actually log of tau A, basically log of tau A.
Right.
It's not modular Hamilton in usual sense. That's right. Yeah.
Okay, got it. Yeah. Thank you. Yeah.
Thank you for the question. And yeah. Okay. So yeah. So here I just will quickly explain some general perspective. In principle, we can formally classify behavior of this reduced transition matrix. And so there is a good class and a more general class. General case is of course quite general. And the best class is actually, in this case, we have a nice information theoretical interpretation. It's like both tau A and tau B, A and B are complement subsystem, Hermitian and positive definite. And the next one is tau A is Hermitian and positive, and tau B we don't get. And C, one more Jaja class is eigenvalue is always positive for tau A, but not necessarily Hermitian. And one more general one is always reigning entropies positive, but this does not guarantee these properties. And this is a more general, it's like just real, not always positive, but just real value. And that. And holographic, if we just talk a single holographic geometry, it's much like this classification B. It seems at least holographic state is within B. And yeah, here it's some exotic state kind of sheets. And if we are interested in more general situation distribution, we can do some kind of numerical analysis. So this is just a well-known entanglement entropy case. We talk about dimension of A is 8 qubits, B is 32, this means 3 qubits, like 8 dimension, and 32 dimension for spin B. And we do just random, sample and calculate entanglement entropy. Then entanglement has a very sharp peak along log of 8, right? It's maximal entangled state, is a volume law-like state has a very sharp peak, but the pursued entropy case, of course, both real part and imaginary part appears. Imaginary part is symmetric, but the real part doesn't look like very sharp peak. I don't know the precise reason for this, but anyway, it's like this way. This complex value is quite general if we just pick up random states. But yeah, I would like to, mainly I'm focusing on state in quantum physics, some pursued entropy in quantum physics. Then it's a different property, as I explained, more simple property. And but before that, so let's try to understand quantum information theory. This is the reason why I mentioned the LOCC. So let's consider class E means this one, best class. Both tau A and tau B are Hermitian, but it's not much more general than standard quantum state, because tau psi and bar phi are completely different, in general different. But in this case, interestingly, we can show following statement: this pursued entropy. This actually turned out to be, we are focusing the case, the pursued entropy is real value in this case. But this real value, actually, we can interpret as a number of desirable Bell pairs, which appears in an intermediate state of post-selection. Psi goes to bar phi. So I'll explain this meaning precisely by proving this claim. So, but anyway, so the state class E, we're talking about this kind of state. Let's take 2-qubit state, and the psi is cosine theta, and this, if this is square 1 over square root 2, 1 over square root 2, this is EPR state, but it's more general, and theta 2 is different. Point is that theta 1 and theta 2 are in general different. So that case, tau A looks like this, and the entropy looks like, pushed entropy looks like this. It's both depend on theta 1 and theta 2. So how we can interpret this in terms of this extra distillation? So for that, actually, we can just follow similar original, proof, original derivation of entanglement entropy as a number of distillable EPR pairs. So we take a M copy of that, This we can just binomial like expansion. So this is a basis projection. This is a basis, orthogonal basis. Pk means like this way. K equals 0. It's like always 0, 0, 0, and k equals 1 means only one of them is 1. Right? One of them is up spin, another is always down. K equals 2 means only 2 of them are up spin, like that way. And their orthogonal state is called P something. P, this we put some kind of index here, 1, 2, 3, and A runs from 1 to combination M1K, MK, and its coefficient is like C1 and S1. And now we do this projection measurement because LOCC, we can allow some local operation, which includes projection. So we projection down to this state, the particular fixed value of A. We fix K by projection. By projection pi K, we fix particular value of K. K is the number of up speeds, like this way. And then, so we do some, and each property of pi K is like weight of pi K is like this, probability distribution. And but if once we assume we just choose particular K, value of K, then we can easily estimate how many Bell pairs can be extracted. It's just log of this guy, log of number of these guys, not these possibilities, number of these possibilities. It's very easy to find such a protocol, right? We could just, it's maximal entangled state, so we can just, for maximal entangled state, it is very easy to distill EPR pairs, like just log of number. But the weight is not trivial. This is PK is not trivial, this weight. And so average value of this EPR pairs is given by this formula. And now this asymptotic limit, that means M goes to infinity, plays very important role. And if we take M goes to infinity, then we can basically calculate this value. And we can in the end find M times this pushed entropy. Pushed entropy is precisely same as this value appears. So that way we can, understand this basic claim. This pushed entropy is measuring some number of distributable Bell pairs, which appears in the psi and bar phi. This is the initial state and the final state, basically. Well, so this is here we assume right? Initial state and final state. Right? We take a probability like that, assuming some post-selection. Okay, so this is so for this special class of state, we have some nice quantum information theoretical interpretation. For general states, it's a kind of future problem. Okay, so these are I'm just here. It's a quite a general perspective. Now I'd like to focus on more high energy motivation target, high energy target, like for holography and quantum field theory. And the holographic case, we are talking about holographic calculation, and already mentioned, it's like a non-trivial Euclidean time-dependent background. We calculate entanglement entropy for subsystem A, and then we have a minimal surface, non-trivial minimal surface. It's not situated on time, so there are no natural time slices in the work. But this is always positive. And that's the basic property we can easily see. If everything is pure, right, A is pure, everything, then no surface appears, it's just this quantity is 0, as already I mentioned general property. And if psi and phi is not entanglement, this is 0. This is actually one way to show this by using AdS-CFT so that we can put some end towards the world brain. So then, and this is subsystem, it's coincide with end towards the world brain, then this surface is homologically trivial, it's just disappear, and just entropy just goes to zero. And we can show SA equals B relation obviously, right? This is the complement is B, so this surface is the same. And we can see also subadditivity, like inequality. But strong subadditivity is not easy, actually. We can see if we naively define strong subadditivity, just naively generalization of SS strong subadditivity is entanglement entropy. It is easy to see to be violated. Right? You can even think this kind of zigzag-like slice is allowed in Euclidean signature. This is not allowed in Lorentzian signature because this is not space-like. But this is Euclidean, maybe you can allow, but this obviously reflects SSA and strong subadditivity. So it's not so clear how to generalize strong subadditivity in this setup for pursued entropy. But yeah, it is easy to prove this, derive this formula exactly the same way as this Luko-Itman like argument of this replicatory. So replicatory is almost same because initial set and final set is just different, but structure is the same. Just put different operator. But other things exactly the same, and we can do some replicatory to calculate this entropy. So that allows us to calculate this quantity in quantum field theory in general. Just slightly more general than, more complicated than entanglement. Okay, so and these are pursued entropy in holography, the general aspect of pursued entropy in holography. But I can give one simple example, like Janus. This is like AdS-CFT-II and the two-dimensional pursued entropy in two-dimensional conformal field theory. But we are talking about Janus solution that is simplest deformation. That means we put some exact marginal perturbation of the ground state of 2D conformal field theory. So exact marginal perturbation has a parameter, right? Phi. So some O is an exact marginal operator, and deformation parameter, we can choose different value of deformation parameter. Initial state, this is defined initial state, and this is final state. This is a boundary CFT gives, and a path integral gives initial state, and this path integral gives final state, with defined by phi. And its dual gravity dual is well known. This is a Janus solution. And the AdS-3 case is a very beautiful solution worked out by Bach and collaborators, like this analytical solution. And we can just use this solution. And the calculation of entanglement entropy is at tau equals 0. And we talked about some lengths, geodesic lengths here. And it is easy to calculate it in the shape of, this extremal surface, minimal surface is the same as usual, but its metric is modified. So in the end, we get non-trivial logarithmic behavior. This is quite familiar. Right? If C over 3 times log L over epsilon appears, this is L over delta means this is well-known formula. But we have a correction factor. This is depend on gamma, and gamma is related to this deformation. So here it's like this way. It's psi deformation parameter depend on gamma, such that gamma equals 0 means no deformation. These are both the same value, phi minus and phi plus. Gamma, if gamma is turned on, these two values are gradually get separated in the exactly given by this way. This is a relation to phi and gamma. Okay, and so if we put if these two initial state and final state is so different, then gamma gets larger, and the effective coefficient logarithmic coefficient gets smaller actually. And you can expand by it's reading on the gamma square, and it's minus appears. And indeed, we can confirm this behavior by perturbation theory and using replicatory dimension. I'm not going to details, but we can. This is quite general property. This is true for any 2D conformal field theory. It goes to minus times lambda gamma square, lambda times perturbation square. So this means that if we perturb ground state of conformal field theory by some exact marginal operator, but also this is also true for any relevant, this is true for a relevant perturbation. So under any perturbation, if you perturb ground state of 2D CFT, we can easily show pursued entropy gets smaller always. It's somehow decreasing. This is actually very decreasing property is quite useful. Also, I will come back here. So this is these are basically analytical calculation by using holography, and we can do some perturbation, but analytical calculation using 2D CFT. But we can do some just direct numerical calculation. So let's try this free scalar model, and then later I come back to spin model, spin system, spin chain model. But here it's free scalar model. So for free scalar model, we have a momentum of x derivative phi prime square and phi square. But we can add one more in addition to mass. We have a mass parameter, but one more we can include one more parameter which is dynamical exponent. Derivative to this power. This is give some non-relativistic dispersion relation, and this is called Lifshitz theory. Actually, our case is very easy to, or our quantity is very easy to calculate for this kind of Lifshitz scalar also. So we are happy to include this, and this is discretized. We do some discretization into lattices, the discretized version. So we have two parameters. So we can anyway for two compute the pursued entropy, we need two different states. So one possibility is different mass, M1, M2. Another possibility is different dynamical exponent, this power of Z1, Z2. We do this. We do calculation of both of them. And so this is now this is a free theory and Gaussian theory. We follow quite a standard technique by using this kind of covariance matrix. I think in next talk, I think Michal will talk more elaborated calculation. But here it's just we can just do some Gaussian calculation. But here's some new ingredient that so we are not computing entanglement. We are computing a pursued entropy. Actually, if we do this, actually there are some non-trivial thing appears, and we need some complexified kind of simplex transformation to simplify the calculation or diagonalize into each element. So we need some one more trick, but the calculation basically goes to parallel. Because as we noticed that the pursued entropy is not everything not Hermitian, right? Reduced entropy is not Hermitian, but nevertheless we need the diagonal to calculate. But that is possible by going to complex valued transformation, simplex transformation. And in the end, calculation is very close to parallel. And this is a technical issue, but in the end, here is just a final plot. So for relativistic case. So let's say Z1 and Z2 equal 1, but the mass is changes. It's in general takes this is a very familiar form, but there are only finite term non-trivial contribution because M1 and M2 is different. It's like this. It's basically this logarithmic log sign behavior appears here. And the generic case, so now G also changes like this way. We can do this. And the mass also changes. And but different
sorry, I got a little confused. So you're computing this entropy for two different states for different Hamiltonians, right?
Different, okay, different Hamilton. That's right. Yeah.
What is the point? I can also calculate for two different states for a given Hamiltonian, right?
Yeah, that's also possible. And you can regard, even though we are using different Hamiltonian, but we pick up both ground state of two different Hamiltonian. But equivalently, you can just fix one Hamiltonian and consider ground state and some excited state.
Okay,
and this is the same.
I see.
Oh, this simple model is these two are the same.
These two are the same. And what would be the point that how do I distinguish it between two different states of two different Hamiltonian, or is that the point by calculating I'll be able to understand how they are entangled or something?
Yeah. So anyway, this quantity depends on two different states. If these two states are same, then it's just standard entanglement entropy. And so we are interested in the difference between this quantity and the standard entanglement entropy.
Right. I see. Okay.
So in some sense, this quantity some kind of measures difference between two different states.
I see. Okay.
But a priori it's not clear. So anyway, we just initially introduced this quantity and its property is not clear. So we would like to study this property by numerical calculations and point out basic property from the beginning. So this is anyway.
Just to suppose I take a CFT and then like I can create two states, say θ1, θ2 acting on vacuum and θ3, θ4 acting on vacuum, and then try to calculate what is their this quantity, as you said, like this pseudo entropy. How is this like? Is it some sense a interpretation of a, let's say that is same as the θ1, θ2, θ3, 4 correlation function in the vacuum, right?
Okay, but it's more, this captures, I think, more something more than I mean local quantity.
Something more than local quantity.
Local. So also entanglement we can capture very non-local, for example, topological phase, which is not probed by correlation function.
I see, but in particular, it can probe correlation function as well as those non-local thing as well.
I think so. I think so. Yeah. I think so. Yeah.
Okay. Thank you.
Right. Yeah. But for this is anyway simple example. This case I'm not completely sure. This is just a Gaussian model. But I'm also if I have time, I'm also going to talk about also topological case. That case is much completely different from correlation function. Actually, it's captured more than that.
Okay. Thank you.
Okay, and yeah, so here, now things are, I mean, non-relativistic also. Z1 is different. But anyway, yeah, so for example, you can imagine some saturation property, like if we increasing, like Z, right here up to here, Z2 equal 1, Z2 equal 2 and 3, but it's actually saturated. There are some, if we see these properties, we find several interesting properties, which I will summarize here. So this is saturation property. So we fix Z1 equal 1, and we fix M1 equal this value. But naively, you might think if it goes to M2 goes to very small, it has a large entanglement. This quantity goes to infinity, gets larger. But it's not that's not true. So it's saturated at some point. Indeed, this value. If M1 and M2 is the same value, it saturates. Monotonically increasing, but saturates. And same thing also true for this dynamical exponent. It's saturated at this point. If Z1 equal 1, so this is Z2. Here it's this type of, this is Z2. Z2 changes, but at Z equal 1, it's just saturated. So this means that this kind of saturation behavior, it's somehow this quantity is bounded by smaller of this among this entanglement. This is a very heuristic, qualitative formula, but this is more precise formula, more something we can say more quantitative way is like this negativity of this difference. The difference already we mentioned. So this is basically, this difference means we calculate pursued entropy and minus averaged value of original entanglement entropy and entanglement entropy of initial state and entanglement entropy for final state. Just take average. So this difference seems to be negative. It's always like as you can see, this plot is always negative for state for this state. So if this inequality, then we might think this inequality is always true. And then so that's I will come back. But here summary, it's so anyway, for excited state and the perturbation of CFT vacuum, if we calculate pursued entropy, it's always satisfy area rho. Because in 2D it's like logarithmic divergence, area rho. And its delta is non-positive, and we have some saturation property. But let's now focus on this non-positivity. And actually, so is this true? Always, it is not true. Definitely not true. This is very special. This means we are talking about very special state. So in general, if we, for example, you can plot this difference in a 2-qubit system, and then it can be positive and negative. Very easy to see. Nearby maximally entangled state, especially this becomes positive. And entanglement is smaller, then it becomes negative for this 2-spin system. Simple. So even this simplest system shows this seems to be very special property. And we would like to basically relate this property to area rho, basically. So area rho means the state is very special. Normally we have volume rho divergence, volume rho entanglement entropy, but area rho has a kind of theory. We are talking about local Hamiltonian and ground state are moderate entanglement entropy than generic one. But we can go further. So when this difference becomes positive, this is the next question. And this is related to this quantum phase relation I will explain. So this is let's take a simplest example, eigenspace spin chain with transverse magnetic field. This is a system we expect a very famous quantum phase transition. Right? This is the eigen Hamiltonian, and J is negative. Then as J is less than 1, the paramagnetic phase. When J gets larger, then we have a ferro, right? Ordered ferromagnetic phase. Right? J equal 1. I'm talking about H equal 1. I'm setting H equal 1. I always set H equal 1. Then J equal 1 is a phase transition point. And then, anyway, initially we do some numerical experiment, but we find something simple actually in the end. So J is smaller. Then, okay, we plot this average. Orange one is average, and the blue one is pursued entropy. So here it's the same point. J1 and J2 equal to each other. Here is the vertical axis is J2. So it's always larger. It looks always larger, but its sign changes here, right? And if J1 equals the same, exactly same as the phase transition point, essentially always a blue one. This is some kind of error. So blue is always lower. Pursued entropy is smaller. This is different. Delta S is negative here, but this is delta S is positive and also positive when J1 gets larger. And so J1 is 2 here, right? So and J2 is also, as long as J2 is in this phase, right? In the same phase, always delta S is negative. But if J1 goes to other phase than J2, then there is a possibility that we can change the sign of delta S. Delta S can be positive. So this is anyway main point I want to argue here. So when delta 1 of delta psi 1 of psi 2 are different phase, this quantity delta S can be positive. And then we can do a more elaborate study for more two-parameter system like XY spin chain. But again, we have same property. Like if these two guys are different phase, we have this delta S can be positive. Okay, and then now I'd like to come to give some heuristic interpretation. This is something already I mentioned in the beginning, actually, but here we have some two states, psi 1 and psi 2, right? And if they are same phase, the difference is negative. This is something we find. And when these two guys are different phase, then this delta S can be positive. And this suggests that actually there is some kind of enhancement of degree of freedom along this interface. And if these two are really topological phases, we can argue there is a gapless mode here, and that enhances entanglement. And that is the reason we have some delta S change the sign. And this here is this is basically the same picture I initially gave in my introduction, but it's more details calculation using AdS space and the Einstein equation. Right. So here we have some different phase, psi 1 and psi 2, and there is gapless mode here. So we have AdS-2 appears. And the Hamiltonian constraint says this equation. This is a curvature of the surface. It's given by Newton constant and some potential of some scalar field. We couple scalar field and minus something, minus kinetic term. So usually, because this minus coupling appears, right? And this gives actually the reason we have always negative delta S. Delta S in general becomes negative because of this minus sign. But here we have a potential. And we can assume potential gets larger here and potential gets larger here and gets smaller because the gapless mode appears and gets larger again. There is some gap to phase. Its potential becomes very large but gets smaller. That's case, this minus sign can overcome this potential contribution. This minus sign can be negligible compared with this potential contribution. And that's case, because of this potential contribution, delta S can be positive. So that's the way. Also, holographic naive argument also seems to be consistent with this picture. Okay. And okay, so this is just one page of this topological pursued entropy. This is related to also previous question, but so good point of entanglement entropy originally is like we can capture a global quantity, right, which is not captured by local correlation function. And this is most of manifest example is like topological entanglement entropy introduced by Pitaev and Plesky and Levin and Wei. So we can pick up the only global quantity by picking up some finite contribution to the entanglement entropy. And we can do the same thing for pursued entropy, so which we call topological pursued entropy. And so we can consider that we can go to the basic example, most of famous example of topological theory, namely 3D Chan-Simon gauge theory, like SUN gauge group. And in this case, we can do replicatory, but replicatory can be easily performed by using Witten's famous surgery method, like the topological only the theories only depend on topology. Right? So I'm not going to details, but just here is some sketch. Right? So we can talk about some state subsystem A and B, and we excite the state by putting anyons, non-abelian anyons, and they are connected by Wilson line in general. And in Zen, so this there are we can talk of different class of state. This is the one anion state, but we can, not trivially wind Wilson lines, and again we get different state, and we can create many different states by putting winding numbers. And we can talk about pursuit entropy between these two different winding number states. Winding number is called A and B. A and B are integer, and we basically need to calculate this kind of grading system, and we just compute the grading partition function. This is actually quite well known in this within Chern-Simon-Gale theory, and some not invariant and so on. It's precisely so. Pursuit entropy is kind of basically log of this such a partition function. And if we plot this here, delta S is the same one. This previous one, this one, basically this one. Sorry, delta S, this one. We plot this. This is interesting, and indeed we can see some A and B winding number is both are even, then nothing interesting. So this delta S is always negative like this. But winding number, difference of winding number is odd, then we have there are chances that actually delta S can be positive. And that means that these two are completely different state and so on. Okay, so this is one example of this topological calculation. I think we can see many other examples. Okay, so basically these are of my talk. So my main claim of this talk is pursuit entropy is the area of a minimal area surface in time-dependent Euclidean area space-time. And this quantity is in general complex valued, but somehow holographic pursuit entropy, which we explain just area, it's always real and positive. And I think, but the reason is very simple, because we are talking Euclidean path integral. And Euclidean path integral creates a very special state because everything is real valued. We assume also real valued sources. So that's the reason, anyway, for this case, we have a nice property. And pursuit entropy, but it's quite interesting to see more general case, but the special case, we argue this is related to quantum entanglement on intermediate states by counting number of EPR pairs. But the natural question, what about general states, especially what's the meaning of imaginary value of this pursuit entropy? This is a future problem. And also we mentioned some relation to a basic property of this pursuit entropy in quantum field theory. Anyway, it satisfies area law as in entanglement entropy, and it's a saturation behavior. And difference delta S is something interesting. And if we talk about single quantum state, some ground state, and some simple excitation, then always delta S becomes negative. But if we talk about two different, completely different states, like if they belong to two different topological phase, then it looks like delta S can be positive. Yeah. And here just several future problems. So this quantum, already mentioned, but what's the complex value of this quantity? And so what about this? In general, we can talk about some complicated gravity dual, and so with some imaginary source, then we get complex valued pursuit entropy, and what's a physical meaning of that? And we might give some, as entanglement entropy gives also powerful tool to constrain, like central charge and so on, like in quantum field theory. So maybe pursuit entropy also gives some such a constraint. And what about the condensed matter and statistical mechanics application? I slightly mentioned this about relation to quantum phase, but maybe also useful for other aspects. And finally, what's about the implication to quantum gravity? So these are future problems. So I think I will stop here. Thank you very much.
Thanks, Tadashi, for wonderful talk. And so now the floor is open for questions. So if anyone have any questions, you can go ahead and ask directly.
Hi, so I have a question.
Sure.
Yeah, so related to this condensed matter physics, do you expect that the pseudo entropy also behaves like the entanglement entropy? Like, for example, if you quench your systems and follow the time evolutions and things.
I see. Yeah. So in my talk, I'm only talking about ground state basically, and to distinguish two different ground states, maybe this quantity is useful. But as you say, it's quite interesting to think of time evolution, non-equilibrium time evolution. For example, under quantum quench, we know entanglement entropy grows linearly under time evolution. So, and what about this quantity? So we have some partial result, and actually in general, so there are some, at least we find some interesting connection between real part and imaginary part. This is in one of our latest paper, but the real part of growth of pseudo entropy seems to be related to some step function behavior of imaginary part of pseudo entropy, and maybe that gives some more hint to understand some non-equilibrium dynamics of kind of quantum systems. But I think it's interesting to explore in future. Yeah, I don't know. I mean, so much about it. It's kind of future.
Another small question. So you did the lattice calculation. So for the lattice calculation, so you need also one-body correlation matrix and find these eigenvalues and things. So the formulas of this pseudo entropy also is similar to this entanglement entropy in that case. Say for the spectrum.
Yeah. You mean calculation?
Yes, for the calculation.
Right? Yeah. Very similar to I mean covariance matrix approach. Let's no, this one. Sorry, I think this one, right? Yeah, basically, these are 2-point function x and r. Basically, we can rewrite. We can just diagonal this kind of matrix, basically. But this is not symmetric, right? Like not Hermitian, not so good property. So we need a generalized diagonalization, basically, and that's of generalized diagonalization.
Okay.
But basically only that. And nicely, in our example, always this eigenvalue, this quantity is always real value. So we get that real value.
Yes, so normally in case of entanglement entropy, also this relation is also true, right? EFX, you evaluate this for half one case. So this so the formula that we are going to use for pseudo entropy is similar to the.
Yeah, that's right. Similar. But actually, we need a justification that formula. That took actually some time because that we cannot diagonalize in usual way. Matrix. This we have to diagonal this matrix into eigenvalues, right? And the usual case, because x and so it's like symmetric. That's good, right? Everything is very simple. We can use just standard diagonalization, but our case we need some kind of non-trivial diagonalization by continuing parameter into complex value. But the final result is very similar. That's right.
Okay, thank you.
I can see one raised hand. Probably we can take one.
Yes, sir. Sir, you found out the adjoint for the pseudo entropy. In that case, are we doing time reversal operations?
Sorry, could you say that again? Sorry, I didn't get the point. Sorry.
In the case of finding out the adjoint of the pseudo entropy, are we doing any kind of time reversal operation between the initial and final states?
So in the definition, original definition, you mean? No. It's just a Brand kit. We don't do any further operation. It's just this one. We just pick up this one.
No, I'm telling when you find the adjoint when we find out, it's I think in the next page.
Next page, okay.
Yes. No, the next page.
This one?
Yes, this one. Yes.
This one?
Yes.
So this is just complex conjugation. I write it dagger, but sorry, this is just a complex conjugation.
Okay, so and there is no time reversal happening there, right?
No. I'm not talking about. But maybe if with time reversal symmetry, maybe we can have a real value. Maybe is that what you want to say?
Yes, sir. Yes.
Okay. Yeah. Right. Yeah. If buffer is maybe time reversal, maybe that's right. Yeah.
And if we have any kind of infalling momentum in the bulk, then will this thing change? Will the adjoint and the if we have some infalling momentum in the bulk, or if we have any kind of change in the stress tensor, if you have any kind of change in the stress tensor in the bulk, will this equation change? Like, because then at that time the time reversal can't be well defined if we have some momentum. So will the
but then, anyway, we don't need time reversal symmetry to define this quantity.
Okay, sir. Okay, thank you, sir.
If you have a symmetry, maybe you have a better property, but anyway, we don't assume it.
Onkar has a question.
Just a quick question, Tadashi. Do you expect your holographic results to also generalize to like quantum corrections or quantum?
Good question. Yeah, naively, I expect yes, I didn't, we didn't study so much, but naively, of course, we expect this quantity, leading term is given by this one, and the one loop correction is pursue the entropy for this region in the bulk.
Right.
And I think probably that's fine. As far as I see this Rukowitz-Mardersen and Faulkner-Rukowitz and Mardersen like calculation. But I didn't check that, I mean, very carefully, so.
Okay, thank you.
Okay, so I think after the coming talk, we'll have some break, 30 minutes. So if you have more questions and hope the speakers will be around, you can ask again after the next talk. So
thank you very much.
So thanks, Tadashi. So we can proceed to the next talk. So hold your question, you can ask after Michal's talk again.
Hey, hi all.
Hi. So yeah, I'm going to make you co-host, then you can.
Yeah, this is what I wanted to ask actually.
Yeah. And thanks for giving the talk. So I know you're traveling.
Yeah, I just came back yesterday actually.
I see. I
prepared in the train.
Oh, I see.
Yeah, let me test one thing before I start. Yeah, does it work? Yeah, as you can see, my iPad, right?
Yes.
Yeah.
iPad and cursor.
Okay, perfect. Good. Yeah.
Okay, so our next speaker is Michal from AEI Potsdam. Welcome, Michal, and he will talk about long distance EOP and RE in CFT. So I will hand it over to Michal to start the talk.
Yeah, thanks a lot for the invitation, and welcome everyone. Thanks for joining me to attend this talk and this session. Yeah, I'm very happy to talk about the paper that we wrote together with Hugo Camargo, who's my PhD student somewhere there in the virtual audience, Lucas Hackel from Melbourne, Alexander Jan from Caltech, and Bennett Vint from Imperial/MPQ in Munich. Where we look at long-distance behavior of entanglement of purification and reflected entropy in general conformal field theories. So in lieu of time, I prepare this talk as a sort of a whiteboard talk. I hope that now you can see my whiteboard. Yeah, excellent. So if I were to sort of zoom out and present this work from some sort of a wider perspective, and sorry, actually one thing that I want to say is that whenever you have any sort of a question, please don't hesitate to stop me and ask it. I mean, I would be very happy if this talk is quite interactive. So to put this work in a wider context, I want to point out basically two phenomena. So on the gravity side, we had several interesting novel gravitational, so geometric observables. For example, the volumes of maximum volume slices, or action Wheeler-DeWitt patches, or volumes of Wheeler-DeWitt patches, right? And this was linked on the QFT side with complexity. And the way it played is that some interesting gravitational observations prompted us to understand a bit better in quantum field theory, quantum information quantity, such as complexity. And similarly, a few years ago, there were two papers that directly motivate the present work. And the story is the following. So now we look at a constant time slice of AdS, right? So we basically take this guy and we just look at from the top. And on this constant time slice, we consider two subregions, say subregion A and subregion B. And now we construct Ryu Takayanagi surfaces in this case, because we look at empty AdS just for definiteness. And now there is a novel geometric quantity that you can define, which is entanglement wedge cross-section. Basically, in this case, the minimal geodesic that connects two Ryu Takayanagi surfaces and lies inside entanglement wedge, which is here. And this entanglement wedge cross-section, so let me use a color here. this entanglement wedge cross-section is an interesting geometric quantity that we would like to assign a field theory interpretation to it. And the conjecture is that entanglement wedge cross-section is equal to entanglement of purification, or an alternative conjecture is that twice the entanglement wedge cross-section is equal to the quantity called reflected entropy. So these are two, say, quantum information quantities that this construction, this conjecture, sort of motivates us to understand better. So basically the topic of my talk is to go back to quantum field theory. You're not gonna really see any holography anymore in this talk, and try to look at these quantities in more detail. If you think about understanding these quantities, you would like to get some handle on them, and a useful handle always is to get a small parameter. And this small parameter is going to be a situation in which we have two subregions that are, say, in the vacuum for this talk, in conformal field theory, yet are very far away from each other. So if you look at the constant time slice of your favorite conformal field theory, this conformal field theory in the case of this talk, for most of this talk, is going to be an arbitrary number of space-time dimensions. And you have a vacuum state there. The situation that we're going to consider is going to be a subregion A and a subregion B that are going to be around balls. Each of these balls are going to have a diameter that is going to be the same. We're going to call it W. And these balls are going to be far away from each other, separated by a distance d. And this distance d is going to be much bigger than the size of the ball, right? Furthermore, what I'm going to assume is that the CFT that we are after, it has a gap in the spectrum of operator. And that the smallest delta, so the scaling dimension of the primary operator, so the smallest delta corresponds to a scalar operator. And the paradigmatic example of a consideration in this particular two subsystem setup is the story of mutual information. So if one considers a mutual information defined by SA plus SB minus SAB. So SAB denotes the fundamental entropy of the union of A and B. It turns out that at large separation, so in the setup of interest, this quantity behaves as some function, known function of the scaling dimension that is not very relevant for the talk, so I'm going to suppress it. But you can find it, for example, in our paper, times W over D to the power 4 delta. And then this formula receives corrections that scale with higher powers of W over delta. So this is a well-known behavior in general CFT, which can be derived using a replica trick. And the only CFT data that this behavior depends on is the scaling dimension of the lattice operator. Now, in a paper in 2020, Orazio Cassini and Pablo Bueno look at reflected entropy in free quantum field theories using numerics based on Gaussian considerations. And what they found out, and for the moment, I don't want to really define reflected entropy, I just want to state the property. What they found out is that the reflected entropy behaves in an interesting way as some number that's going to be theory specific. They checked this for free fermion and for free boson, and this number was different. So let's call this number hash naught. W over D to the power 4 delta. So this behavior here is very similar. I mean, it's the same as the one we've seen for and understood for mutual information. But then there is an additional contribution multiplying this, which is a logarithm of basically distance over W. Let's write it like this. And then there is a subleading correction that they also established by fitting to the numerical results. And this subleading behavior is basically some offset. So some number. Basically the topic of this talk and the topic of the work that this talk is based is to provide a really simple derivation of this behavior of the reflected entropy, and at the same time of the behavior of the entanglement of purification and the large distance limit in arbitrary CFT, which is this logarithmic enhancement of the scaling by a logarithm of the distance over the size of subregions. So basically proving this formula both for reflected entropy and, as it turns out, for entanglement of purification is the goal of this talk and the topic of the paper that I mentioned at the beginning. Are there any questions about this?
So one quick thing. Do you know what is the analytical expression, corresponding analytical expression for the purification? I mean, like this what you wrote for this reflected entropy.
Good. I will talk about it.
Oh, I see. Okay. I see.
So that's a good question. I'll talk about it. Yeah.
I see. Okay.
Yeah. Anything else?
I see. Proceed. Perhaps continue.
Good. Yeah. So I told you about mutual information. You probably knew better than myself how it scales with a distance in the large distance separation. It's a classic result. But I told you what is the expectation, what is the formula that we want to prove, which is the formula for mutual information times the logarithm of the distance, or logarithm of the mutual information. But I haven't really told you what entanglement of purification and reflected entropy really are. So like this is basically the source of Arpan's question. The important thing to note is that both reflected entropy and EOP are some measures of correlations in mixed states that are defined in terms of purifications. So, well, I mean, like purifications are hard to work with in the context of quantum field theory because you basically have to enlarge your Hilbert space and seek for pure states in this enlarged Hilbert space. So this makes the dimension of the total Hilbert space bigger, and at the same time you might be running into all sorts of trouble related to UV regularizations and so on and so forth. So for the purpose of this talk, we're going to be always assuming, or I'll be always assuming, that a given CFT can be regularized, UV regularized in terms of a lattice description, in a similar way in which Ising CFT can be regularized in terms of the Ising model, so the model of spin 1/2 described by a local Hamiltonian. So To put everybody on the same footing, let me discuss a purification. A canonical example of purification is a thermophile double state. So an example of a purification is a thermophile double state. So the idea is that we start with a thermal density matrix. So Z beta is related to normalization, is just the partition function. And we sum over eigenstates. We have e to the minus beta e. And we have basically projections onto an energy eigenstate. So we sum over the whole spectrum of a given theory. Let's call for definiteness this theory a left theory for the reasons that is known for most of you. And basically, a thermophile double state is defined as a square root of this expression. Thermophile double state is going to be given by a square root of Z beta, sum over the energies. Here the Boltzmann weights are raised to the power 1/2. But now an important difference is that this is a state in the enlarged Hilbert space in which we took another copy of our physical system and we define a pure state in the Hilbert space that is a product of the Hilbert spaces of our original system and its copy, right? So this is a thermophile double state. And because of this, because of these square roots here, I'm going to call it as a particular purification of the density matrix that I'm going to denote by a square root of rho. So that's a purification of our thermal density matrix that I will refer to as the canonical purification. And now it shouldn't come as a surprise, and this is why I gave this particular example, that the same construction goes through if you don't consider the thermal state, but if you consider any density matrix in any physical system. That is, you can always find this square root of rho purification following the same procedure as you follow for thermophile double state. And now the important thing about basically the defining feature of the thermophile double state, of course, is that if you take the trace of the density matrix of the defining by the thermophile double state over the auxiliary system that I denote here as the right system, you recover the thermal density matrix, right? So that's basically what purification has to do. So now, imagine now that our rho that we start with is actually a bipartite system in a mixed state. So our rho consists of two parts like A and B. And the idea that you have to have in mind is that our rho, in this case, can be the reduced density matrix in A and B subsystems in this figure, right? And now when we purify, say, to a state that I'm going to be denoting as a square root of rho, this means that we're going to have A, we're going to have B, but we're also going to have a factor that I'm going to be noting as A prime and B prime, right? Which are basically reflections of A and B in this right system, the system that is a copy of our original Hilbert space. And now what we can do is we can define the reduced density matrix in A and A prime by tracing over B and B prime. And having done so, the definition of the reflected entropy is that this is just the von Neumann entropy of this density matrix in A and A prime. So basically the idea is that we start with a density matrix, we construct the canonical purification using the thermophile double like construction, we trace out the B, so like 1/2 of the original system, and its reflection, so B prime, and we calculate the von Neumann entropy, and this defines for us the reflected entropy. Now, for the entanglement of purification, the story is a bit more involved, because what we can do still when we purify is we can define a family of purifications that start with our canonical purification and act with a unitary operator on A prime and B prime, so the factor in the Hilbert space that we purify with, and identity on A and B. And this defines for us a state that I'll be calling throughout this talk, say psi. And now the EOP, so entanglement of purification, is defined as a minimization over basically this unitaries of SA A prime evaluated on psi, right? So the story is the following. We have a density matrix for a bipartite system. We purify it to a thermophile double state. And then we have two choices. Like, we either take directly a trace and define a reflected entropy, or we still act with an arbitrary unitary in this purifying Hilbert space, and then we take a trace and minimize over different unitaries and define entanglement of purification. So entanglement of purification is a more challenging quantity to consider because of this additional necessity of optimizing over all unitaries acting in the auxiliary Hilbert space. And of course, this is also a part where the challenge lies in defining this quantity in quantum field theory, because you have to optimize in quantum field theory over unitaries acting in some auxiliary factor. So there's a reflected entropy, which is simpler. There's entanglement of purification that is more involved. And it turns out that both of these quantities obey a very powerful and useful for us inequality, which is that entanglement entropy of A prime is bigger or equal to 1/2 of the mutual information between A and B. I think I've been noting this as A. So this inequality can be derived using strong subactivity of the entanglement entropy. And because here what sits is entanglement entropy A prime, it turns out that on the left-hand side we can either put reflected entropy or EOP, and this equality is going to be obeyed by the both of them. So to wrap up, like, we're gonna be this part, we're gonna be considering a mixed bipartite state. In this mixed bipartite state, we're gonna be interested in studying two quantities measuring correlations between A and B. One is reflected entropy, the other one is entanglement of purification. Both of these quantities are defined in terms of purifications, both reflected entropy and entanglement of purification obey an inequality, and this inequality tells us that they have to be bigger than half of the mutual information. And this inequality is going to be crucial because that's going to basically allow us to derive the behavior of both quantities in arbitrary conformal field theory in a very elementary way.
Michael, just a curiosity, is it also good measure for a tripartite system, or is it only good for bipartite systems?
You're asking if you can use reflected entropy or entanglement in the context of tripartite systems.
For example, thermophile double to thermophile triple, example of that kind.
I have not thought about it, so sorry. I mean, I don't have a good answer to this question. Maybe we can leave it for subsequent discussion because maybe somebody else has something interesting to say about it. Yeah, but thanks for the question. Anything else? Okay, good. So So the starting point of the actual analysis in the paper is the following. It's very simple, and it is that when we consider a density matrix in so maybe let me draw it again, or maybe even I can do better and copy it. Yeah. So the starting point of the analysis in the paper is that if we consider the density matrix in AB at large separations on the lattice, if we take our systems to be infinitely far away, then we're gonna get a product density matrix between what is the density matrix in A and what is the density matrix in B. In this case, the mutual information is going to vanish, and this is indeed like the case with it because of its parallel fall-off. At when D is infinite, then it goes to 0. And then there are corrections to this description, and these corrections to this description of product density matrices are basically the stuff that is important to us. That is the stuff that governs the correlations between A and B as encoded by correlation functions of local operators in the CFT, as well as encoded by the mutual information and in our goal, which is the EOP and reflected entropy. So the first correction to this product of density matrices is going to come from W over D to the power 2 delta, where delta is the dimension of the lowest lying scaling operator in the theory. And then there's going to be some density matrix that I'm going to denote by some contribution to the density matrix that I'm going to denote by rho AB1. And the only thing that I'm going to assume about it is that it's Hermitian. And then there's going to be further corrections, like with weaker scaling with the separation. In particular, there's going to be a term that goes like W over D to the power 4 delta. And I'm going to follow the notation of the paper. And then there's going to be even further weaker terms in the expansion. And now the idea is that, for example, this term is going to be a term that cares about a correlation function if we insert one copy of our operator O delta, so like the lowest lying scaling operator in A, and the other copy of the same operator in B, right? And if we calculate the expectation value of this product of operators, this contribution to the density matrix is going to be the one that is responsible for the leading fall-off of this quantity. And a similar logic can be also applied to other terms in this expansion. Now, there is one more important property of these matrices that it turns out that is not really articulated in the paper, but is going to be relevant for whatever I want to tell you, which is that if we consider rho A or B, doesn't matter, so like one of these two guys, they arise as a trace over A or B of rho AB, of course, right? And if you want to fulfill this property, it turns out that what you want to require is that the trace over A or B of rho AB, 1, 2, etc., it has to be 0. So this is the property that that comes from this definition of what we mean by the reduced density matrix. Because in this case, you just want to get a contribution from the first term, and you want like all the rest in this complicated sum to drop out. And with this insight, what I want to show you is how to derive the known scaling of the mutual information with the separation, and then repeat the very same logic in the case of reflected entropy and entanglement of purification to show you that the proof of the behavior of the of these more novel quantities, less understood quantities, is actually very simple and very similar to what's been known before. And in order to prove the behavior of mutual information at large separations, let me invoke the first law of entanglement entropy. And the first law of entanglement entropy says that the entanglement entropy of the density matrix, that is a perturbation of some other density matrix, to the leading order in this perturbation is given by, well, we get like the old answer. And the correction actually is going to be given by trace of minus log of rho delta rho. And then there's going to be terms that are of the order of delta rho squared. So what we are going to consider is that our rho, in this case, is this rho A tensor rho B. So it's the leading term, it's this term in the expression that I showed you. And our delta rho, for the moment, is going to be this guy over here, which is the first correction to the long distance behavior of the reduced density matrix for the bipartite system in the vacuum of a conformal field theory, which is, you know, this W over D, the power 2 delta, delta rho 1. I think I'm consistent with, like there's still AB. So when you look at the math and you consider this term, what the logarithm of the density matrix gets you when you look at this expression is going to be a sum of two contributions. So one contribution is going to be minus log of rho A tensor, sorry, minus log of rho A tensor identity in B. And the other term that you're going to get is minus log of rho B, so a modular Hamiltonian in rho B, that in fact for a conformal field theory is known in a closed form, tensor from the left, identity in A, right? We get this guy, and we have to take a trace with respect to AB. And we have here this delta rho 1 AB. But note that we're taking a trace with respect to A and we're taking a trace with respect to B. And this delta rho AB is like its trace with respect to A and or its trace with respect to B vanishes. And here, because of these identities present here and there, the result is going to be just 0. So what we know from this is that the leading possible contribution to the mutual information that comes from the connected part of the density matrix between A and B, it vanishes by the virtue of this condition. And remember that in the story of this density matrix expressed as a series in W over D, there are possibly terms sitting over here that might come from not lowest primary operators. And you can, as it turns out, you can run the same argument also for these terms. And then entanglement first law also has corrections that are of the order of delta rho squared that I have not really written here. The reason being that they are rather complicated, because delta rho and rho do not necessarily commute with each other. And as a result, you have to be very careful and use Becker-Campbell-Hausdorff formula. So in the end, like what we expect is that S, or what we know actually, is going to scale like delta rho squared. So basically, it's going to scale like W over D to the power 4 delta, or slower. So this is what such a high-level argument tells us. But on the other hand, there is an inequality that is important and well known since 2007, which is that the mutual information between A and B is bigger or equal than some number, that's not going to be some C number, times expectation value of the correlator squared. And this expectation value of the correlator squared for O, A, and B being an operator inserted in A, an operator inserted in B. Sorry. So let's take as this operator an operator of dimension delta. This is actually going to give us W over D to the power of 4 delta. So what we know from this is that the mutual information scales actually at least as W over D, whereas from the previous analysis, we know that it scales as at most W over D to the power 4 delta. So by combining these two insights, we actually prove in this way that this has to be a scaling of the mutual information with the separation between two subsystems. And indeed, like if you do a more detailed CFT study using replica trick, you do derive this formula from OPE of twist operators. And what you get on top as a bonus is a prefactor in front, which is a closed form expression involving gamma function of delta, or of some linear expressions in delta. So
one thing is that so the mutual information has these 3 terms, right? As SA plus SB minus that thing. So you still expect order rho square term will not cancel somehow magically.
Yeah. So the term that you mentioned. So the first 2 terms, SA plus SB, are taken care of by this contribution.
Oh, I see.
I don't care about this contribution. This is the boring contribution.
I see.
Because it comes from the product of density matrices. Thanks for the comment. Like what I'm looking at is the interesting contribution that comes from the connected part of the density.
Oh, I see.
Yeah.
That is coming from the AB part, but the order rho square part of the AB is AB part in the mutual information. I see. Okay.
As well as the square of the order of the leading order contribution to connected estimate.
I see. Thanks.
Yeah. So basically, I presented to you not because I doubted that you know it, but just to give you a taste how to derive large distance behavior of the mutual information in conformal field theory using an argument that starts with the form of the density matrix that we expect based on OP, and then using an inequality bounding the behavior of the mutual information to get that the behavior that mutual information along separations has to obey is basically the leading behavior that this argument predicts. Because of course the loophole in this argument can be that the coefficient in front, so the coefficient here is 0, but if it were 0, then we would have violated this inequality, and we cannot. So we know that the coefficient is non-zero, and that this scaling holds.
I see.
Good. So that's a natural breaking point. So if you have questions, like please go ahead and ask them.
I see. Please go ahead.
Yeah, very good. So the rest is actually surprisingly simple. So we were really so the way like we came up with this was by first doing analysis using numerics, and later actually zooming out and like trying to understand the analytics or like the analytic understanding of these numerical studies and numerical observations. So again, like just to bring everybody on the same footing, like we're gonna start with the situation in which the density matrix to the leading order at large separation is a product, And then we're gonna get a behavior that is W over D to the power 2 delta. And I'm gonna denote this as epsilon delta. So it's a small parameter. And there's gonna be this connected contribution to the density matrix that in particular captures 2-point functions of the lowest lying scaling operators. One inserted in A, the other one inserted in B. And then there's gonna be a correction, and I'm gonna focus on the correction that is quadratic. So that goes like epsilon squared, rho AB2. And then there's gonna be other terms that either gonna be higher order or gonna be irrelevant for this analysis. And now, since the expression for the density matrix is perturbative, and let me emphasize that it's not perturbative in the sense of the coupling constant, but it's perturbative in the separation between subsystems, then it is natural to seek for the purification also in a perturbative way. So what we want to do is we want to study a purification to a system in AB, A prime, B prime. And for the moment, you can just think about A prime and B prime as being mirror images of A and B. And the total dimension of Hilbert space in A prime, B prime is the same as in A and B. And then this purification is gonna consist of a contribution coming from the zeroth order. So this guy is gonna be a purification of this term, right? Then there's gonna be a contribution from the first order, so there's gonna be epsilon delta, psi 1. So this guy is gonna be talking to that expression, sorry. And there's gonna be also a term that goes like epsilon delta squared, psi 2. And this one is gonna be talking to, change color. This one is gonna be talking to this thing, right? So we're gonna be looking for a purification perturbatively in this epsilon delta, so like 1 over the distance to a power parameter. And now, an important thing to notice is that this zeroth order purification, because the density matrices that we started with are product of density matrices, is also going to be a product of state. Is going to be a product of a state that is defined in A and A prime times a state that is defined in B and B prime. So that there's no entanglement between A prime, and B prime. And this is to be expected, right? Because at large separations, we expect the entanglement of purification and reflected entropy to vanish. So everything is consistent. And now, of course, we're going to be considering corrections. So like we're interested in deriving like the form of psi 1 and the form of psi 2. But the beauty of this argument is that the precise form of psi 1 and psi 2 is not going to be really needed for our analysis. Like the only thing that's going to be relevant is that when we find our perturbative purification, we're going to be studying the reduced density matrix in A prime, because this is the quantity that enters the definition of the reflected entropy. And this density matrix we're going to represent in a diagonal form as some mu naught, mu 1, well, all the way to the last of them, not very relevant for us, but let's call it mu n. And indeed, like this is the faithful way of representing it on the lattice, where the Hilbert space is finite dimensional for subsystems. But at zeroth order, so for terms that are of the order epsilon delta to the power 0, our state, our purified state is a product of a state in A and prime and a state in B prime, pure state in B prime, as a result of which, like mu naught is 1, we can take it to be 1, and mu j are all 0. So the fundamental entropy, of course, is going to be 0. At the order of, epsilon delta, we could get some corrections. In particular, what we could get is for this mu j's bigger than 0, we would get that they come with some numbers times epsilon delta. An important thing for us is that these terms here have an interpretation of probabilities based on the how we understand the density matrices. So we would like to impose that these contributions are actually always non-negative. However, if we regard epsilon delta as a formal parameter, we can take this epsilon delta to be positive, or we can take it to be negative. And if we take it to be negative, these contributions get negative, so we cannot really interpret them as probabilities. So as a result of which, we don't expect any contribution at the order of epsilon delta. And now, if there's going to be a high order contributions, so there could be contributions of the order. The next order is going to be contributions of the order epsilon delta squared. And now, basically, in this case, this mu naught is going to can be written as the following term, and mu j's are going to be written as some alpha j's, epsilon delta squared. Alpha j's are bigger than 0, and alpha tot are bigger or equal 0. And this alpha tot comes from total, is a sum over all j bigger than 0 of alpha j. So what I'm trying to argue is that this is the lowest permitted contribution to the eigenvalues of the reduced density matrix in this perturbative purification. And it starts at the order of epsilon delta squared.
Sorry, so this argument also comes from the fact the scaling of the mutual information, right? You say that it has to be grow as some epsilon to the power that factor 4d, because if you compute again mutual information between various a prime and ab prime, that also you want to scale like what you showed before. And
so what I want to emphasize is that there is a relation to the relation to the mutual information is there, but it's only there at the level of this density matrix, reduced density matrix in A and B.
Oh, I see.
Because this is the quantity for which you define the mutual information in conformal field theory, right? Now, you can also play with mutual information for, say, a prime, etc., etc. But you don't have to. I mean, it's not what the previous argument was about. This is an independent argument that has a structural similarity to the argument for mutual information, but it's more at the level of analogy rather than at the level of exactly the same kind of derivation.
Oh, I see.
But anyway, the important thing for whatever I have to say is basically the definition of the fundamental entropy. So we're going to be interested in calculating EOP, or reflected entropy, and this is defined in terms of entanglement entropy between A prime, and this is given, of course, by definition as a sum over the eigenvalues of the density matrix of this guy over here. Sorry. And now, if you look at these expressions, if you just plug the form of the eigenvalues that you get, it turns out that as A prime is going to be this coefficient alpha tot. So this guy over here times epsilon delta squared log epsilon delta minus 2 plus some offset. And I'm going to suppress it because I don't want it to get it even more technical. Epsilon delta squared. So this is the behavior that our formula predicts as the leading order possible behavior at large separations. So just to remind you, epsilon delta is W over D to the power 2 delta. Okay. Now mutual information scales as this some function of delta times W over D to 4 delta, as I showed you, which is nothing else than epsilon delta squared. Okay. And now, as I indicated earlier, there's a simple inequality that you can derive using strong subadditivity, regardless if you consider entanglement of purification or reflected entropy, which is that SAA prime is bigger or equal than 1/2 EAB. So now going to our formula, what we see is that EAB scales already as epsilon delta squared. And here for reflected entropy or entanglement of purification or any SAA prime, we derive that in the leading order, it scales at least as epsilon delta squared. Perhaps it scales as higher powers of epsilon delta. But the important thing is that it cannot scale as an even higher power of epsilon delta than epsilon delta squared, because the mutual information that scales as epsilon delta squared provides for us a lower bound for this quantity. So as a result, we know that SAA prime has to have this form epsilon delta squared log epsilon delta minus 2, which is nothing else than this behavior that I advocated at the beginning, which was found for numerically for reflected entropy by Bueno and Cassini. So what I have shown you is a very elementary derivation based on the perturbative structure of the two subsystem density matrix in the vacuum of arbitrary conformal field theory that both reflected entropy and entanglement of purification necessarily behave as a mutual information at long separations enhanced by the logarithm of the distance. So this basically explains, at least in mathematical terms, the emergence of this logarithm of the distance, mysterious logarithm of the distance, that Bueno and Cassini saw in 2020 in their numerical studies. And this proof is very simple very simple and very similar to the way you can prove the long distance behavior of mutual information with a distance. So one thing that we have not, this argument is not really capable of providing at this level is the value of the numerical prefactor that sits here in front. And this is where numerics can help. Yeah. So what we did in our work is we considered two examples of quantum field theories described on the lattice by lattice systems. One example are Dirac fermion CFT, which is described by free fermions on the lattice. The other example is an Ising CFT that is described in terms of the Ising model. The left column, free fermions, are Gaussian studies. The right column are studies in terms of spins are intrinsically non-Gaussian. And we look at subsystems of sizes between 1 side to 3 sides at very large separations, so for very big systems. And what we see is that already for a single side subsystem, we see a reasonable convergence to the continuum prediction for mutual information that is known in a closed form. And for 2 or 3 sides, it's basically spot on with the prediction of the exact analysis. And similarly for Ising spins, actually there already for one side, one is very, very close to the analytic prediction from replica trick for the large distance behavior of the mutual information. And now for reflected entropy, these are the studies in the case of free fermions by Cassini and Huerta. So we reproduced these results and we noted very good agreement. And indeed, we were able to derive also the coefficient of the leading fall-off as well as the offset. Similarly for the Ising spins, which is a new prediction because it relied on the study that was not Gaussian. And for EOP, the analysis required, on top of constructing canonical purifications, it required also acting with a unitary in A prime and B prime and minimizing over this unitaries numerically. And we were able to do this and obtain results that signal convergence to continuum, and the relevant numerical factors we quote in this figure. So basically, it's time to wrap up. So let me summarize. Reflected entropy and entanglement of purifications are challenging in quantum field theory. Well, it's at least like before we started this project, like we thought that it's going to be very hard actually, especially for entanglement of purification, to come up in the regime we're interested in with any sort of argument or proof for its behavior. However, nevertheless, we're able to show at the level of a physics proof, I would say, for a general CFT in arbitrary number of dimensions that reflected entropy and entanglement of purifications behave as at large separations as mutual information times logarithm of the separations, so logarithm of the mutual information. And this behavior, although we didn't know it in the first version of the article, this behavior was seen in the studies of reflected entropy numerically by Bueno and Cassini for free quantum field theories. And the key idea for our study was to introduce a small parameter, as often is the case in physics. And the small parameter was to view the density matrix for two subsystems as a product of density matrices plus perturbations. And doing perturbative analysis allowed us to identify the leading possible contribution to the reflected entropy and mutual information, and then used strong subadditivity basically to show that this leading contribution to reflected entropy or entanglement of purification has to be the contribution, that is like the first non-zero contribution, which basically establishes this this long distance behavior here. And in the paper, having established a general result, we turn to numerics to predict numerically the form of the prefactor here. So like we also predict the prefactor here for free fermions in 1+1 dimension, and for the Ising. And for EOP, this was actually quite challenging because this required optimizing over purifications, which for Ising were non-Gaussian purifications. So this is basically what we discussed in the paper. There are two things that, at least to me, seem very interesting and possibly promising open directions. So one of them is is to understand what is basically the prefactor in EOP and in reflected entropy as a function of CFT data, in particular as a function of the lowest lying scaling dimension. For entanglement of purification, it might be challenging because this requires doing this optimizations of purifications. So my hopes are not very big there. But for reflected entropy, because one considers these canonical purifications and one does not need to do much with them, just take some traces, maybe it's possible actually to use the sort of argument that I'm outlining here to derive this prefactor in a closed form. In particular, in the paper, we have a very neatly looking formula for this prefactor in terms of our construction, but not in terms of CFT data. And the other thing that I find interesting is this logarithmic, this additional log of the distance, so the log of the EAB. I mean, typically in a CFT, you would expect to get like a parallel follow-up of quantities that you can relate to some simple correlation functions. Here we get like this logarithmic enhancement, and it would be very interesting to understand the origin of this logarithmic enhancement more in physics terms, as well as to perhaps provide maybe a tensor network understanding of such a contribution coming, for example, from a MERA perspective. So that's all that I had to say. Thank you very much for your attention.
Thanks, Michal, for the wonderful talk. And now the floor is open for questions. So if you have any questions, you can please go ahead and ask. Right. I thought there is a question in chat. So if it's a present, you can ask directly.
Sir, I had a question.
Yes, yeah.
If there's an increase, if there's an increase in complexity in any one of the systems A or B, will there be any perturbations in the density matrix?
Well, I'm not sure. I have not really talked about complexity. I mean, you can define similarly to discussion of reflected entropy or entanglement of purification, which we start with a mixed state and you go to a pure state, and there in this pure state you define a genuine measure of entanglement, which is entanglement entropy. Similarly, you can consider a mixed state purified and use a definition, your favorite definition of complexity, to describe it. And to the best of my understanding, like, such things have not been done in the literature. So I would say that your question is an open research problem.
Okay, thank you, sir.
So also I'd like to remind that if you have any question for Tadashi also, you can ask both of them now. We have some buffer of like 20 minutes or so for the next talk. So please feel free to ask any kind of questions. So okay, so I have a nice questions because so when in the reflected entropy part, it is not necessarily considered only thermal state, right? I mean, any excited state, I mean, one can create any excited state by operator insertion, then use the reduced density matrix, then you can do this operator state map to find the corresponding state and compute the reflected entropy, right? Is that right? Or
yeah. So I just presented a thermal density state, density matrix as an example that is accessible to everyone without any background in this area. But the construction is purely formal. So if you give me a density matrix, at least for 1 or 2 spins, I would certainly be able to do this exercise.
Oh no! I was asking because your last comment actually, because you said that reflected entropy, that coefficient as a function of the conformal dimension delta. That is why I'm asking that some operator with some conformal dimension, say primary operator, some conformal dimension delta, I act on the vacuum and then construct the density matrix and do this for various of such family of such operator, and whether I can fix the coefficient as a function of delta, something like that actually.
Okay, so this is a good question, but I think we might be talking about two different things. So like for me, the thing that I was interested in, or like at least like I elucidated in this talk, was that we have like these very complicated density matrices for subsystems. Well, actually, maybe I shouldn't say this, right? Because like in conformal field theory, we know what they are, because for a spherical subsystem in a ground state of conformal field theory, we know that the logarithm of the reduced density matrix is going to be given by the modular operator, whose form is basically a smeared stress tensor with some known smearing kernel, right? So like these guys are not as complicated as they are outside CFT and for non-spherical subsystems. Now this contribution over here that I'm trying to make a bit thicker is a contribution that is responsible for non-vanishing connected correlation functions for operators, one operator inserted in A and the other operator inserted in B. So this guy certainly cares about delta, but it's more than this. In particular, if your operator O delta has a non-vanishing 3-point function, either with itself or some other operator, it turns out that this 3-point function is also going to be encoded here. 2 insertions in one subregion and 1 insertion in the other subregion.
Oh,
so
I see.
So this guy over here, this rho AB1, is actually complicated, and it cares about various properties of OP. However, it doesn't care about everything. I mean, like it just cares about insertions of two light operators in both subregions, and and you cannot really have, I think, heavy operators inserted in both of them. Like I don't really have it formalized at this level, but what I'm saying is that it cares about some CFT data, but not all of the CFT data, or not all correlation functions rather, and so on and so forth, right? So if one were to sort of formalize whatever I'm trying to say now into some concrete expressions, then at least for reflected entropy, one can try to establish this coefficient alpha tot. So this guy over here, in terms of the CFT data encoded in delta rho 1. But we have not really done it. It was beyond the scope of our work. The scope of our work was just to look at this asymptotic behavior and match the functional form, derive the functional form, not the prefactor.
Oh, I see. Oh, I see.
Sir, I have another question.
Okay. Yeah, sure.
Sir, the perturbations are due to the change in the distance between the two. Are due to the change in distance between the two systems, right?
Yeah. So the perturbations are what I mean by the perturbation is not a perturbation in state. I mean, like, we consider the system to be in the vacuum. What I mean by the perturbation are correlations between A and B that are encoded in the density matrix, not being a direct product between the density matrix in A and density matrix in B. So whatever comes on top of a direct product in A and B is going to be my perturbation.
Okay.
But the thing is that because of this assumption of the gap in the spectrum of operators, I could identify the leading perturbation that comes from the lowest lying operator, in this case assumed to be a scalar operator. But I would expect the proof to go the same way if the lowest lying operator is not a scalar. In particular, for free fermions, the lowest lying operator is a free fermion operator, unlike psi or psi bar, and it's not a scalar. Yet the behavior of the formula is precisely the same as we got in the high level analysis. So I would expect it goes through for any operator, just given the gap in the spectrum and being on lattice, because we want to, I mean, like in particular here, yeah, here, you know, like we diagonalize the density matrix, right? I mean, this is something that works very, very nicely when you have a finite dimensional Hilbert space in subsystems, and this calls for a lattice. I mean, if one were to look at continuum, I'm not sure if such a clean argument can be made.
Okay, thank you, sir. Yes. Okay, thank you.
Yeah, thank you for the question.
Any more questions? Please feel free and go ahead if you have any more questions. If not, then I thank Michal for the talk again. Thanks, Michal, the talk.
Thank you.
Okay.
Do you plan to upload slides also to the website, or not really?
So actually, we didn't ask the other speaker, but you sort of posed the question, so maybe. So is it possible if you can send this because you have written this a handwritten note, so I think we can upload it with the video slide. That will be better. So
okay, yeah, I'll do that. I also have some sort of a script. I'm like, it's not visible.
Oh, I see. Oh, I see. Oh, that will be good. Then please email that actually. So that will be good.
Yeah, I will do. Thanks.
I think so. I will hand it over to Shubha for the next session. We have, I think, 15 minutes. 15 minutes window to start that off.
I'll pause the recording so people can engage in any discussions if they want off the recording.
Yes.
Yeah, please go ahead.
Okay, so first of all, I would like to thank the organizers for giving me the opportunity to present our work. So I will be talking about Q curvature and its relation with path integral complexity. This is based on our upcoming work with which will appear soon with Hugo Camargo from Albert Einstein Institute, Potsdam, and Pavel Caputa from University of Warsaw. So rough plan is as follows. First, I will review the concepts of path integral complexity, especially the optimization procedure. I will not go into the details as Pavel had already discussed in detail yesterday. I will just review for the sake of completeness and just connect with some later discussions. Next, I will formulate the optimization procedure as an uniformization problem. This will help us to introduce some quantities known as Q curvature, and we'll see that how this will help us to understand the optimization procedure in more general way. Then I will discuss it from gravity side. And finally, I conclude with some results and remarks. So last but not the least, due to time constraint, I may not be able to discuss everything thoroughly, but I will try to give an overall picture and a general message. So feel free to interrupt me in between if you have any questions or comments. So first we'll discuss path integral complexity. So it's a different approach on complexity based on Euclidean path integral. Normally you define circuit complexity by Nielsen's approach, which is based you take some, you want to build some interior operators, and you want to consider some set of gates and some error tolerance, and you want to build some interior gates. And here this is a different approach, but our goal is to prepare a CFT ground state with some optimization procedure. So this is basically optimization procedure to prepare ground state in the arbitrary dimensions. So the optimization corresponds to minimization of certain functional with respect to the background that we are going to integrate. And this functional in two-dimensional is basically known as the Liouville action. So the detailed procedure as follows. So first of all, how you prepare a ground state in QFT. So you carry out a path integral in Euclidean time. So these minus z is our Euclidean time and special coordinates x. for the boundary condition, that is our boundary condition, that we are going to prepare our states at z equals to epsilon, and that's why we're going to integrate from epsilon to infinite, and this is our boundary condition that so that appears in the page configurations, and this G is our background metric with some appropriate actions. These are boundary conditions, and this metric we usually take as a flat. So mathematically, the optimization corresponds to this equation. So you have some background metric, and you want multiply some conformal factor, or especially in the wild scale scaling with some uniometric and with some phi. And this is your you do the path integral over this new metric with the and you also do the path integral over your old metric, and these are related by a proportionality factor, this exponential of phi of G, which is only depends on the reference metric G hat and the field that we are do the wild scaling. So path integral complex. So when you get this factor, so your next task is to minimize this functional with this phi. So you minimize this functional phi, and you get a particular solution of phi naught, and you plug that phi naught into this I. That is basically you are calculating this on-shell functional, and this is known as the path integral complexity. In two-dimensional, you can directly identify this path integral as a Liouville action. So here is a Liouville action. So you are integrating over epsilon to the infinite. This is the central charge, and this is two terms. One is the kinetic terms, and one is the potential term. So and the mu is the Liouville potential here. So this is the other Liouville action in two dimension, and this is the path complexity action in two dimension. Okay, so let's go deeper into two dimension. So two dimension, you start from a flat matrix. So you have a Z and the X, and you want to consider what kind of matrix you can choose for this new metric, like this metric. So it turns out that in two dimension, any metric you can choose as a conformal equivalent to this flat metric. So you consider a kind of metric like the 2 pi with the appropriate boundary condition that z equals to epsilon. The factor should reduce over 1 over epsilon square. After that, you want to solve this equation. So basically, you are carrying out this functional. You want to minimize this function with respect to pi, and you get the solution of the form to the power 2 pi 1 over z square. So that leads to the optimal metric as 1 over z square. This is e to the power 2 pi factor, and this is a hyperbolic metric. And on the solution, you can calculate the Liouville action. Basically, the on-shell Liouville action is your path integral complexity. So that is basically it should be noted. Two factors should be noted. One is basically proportional to L, and is proportional to 1 over epsilon. So L is basically this shows the volume law scaling, because in two dimension is a proportional to L, and epsilon is because it is dimensionless. I'm going to factor by 1 over directions. So that's the path integral complexity in two dimension. Now you want to see if we can. So natural question arises: what could be the complexity for higher dimensions? So for that, we need to let us formulate the problem in different way. So in the Q curvature problem. So normally this is a uniformation problem that is basically known to the mathematics literature much, and also in the physics literature. So you can find the reference here. So the problem you want to consider a compact even dimensional manifold M with a equipped with a metric G hat AB, and you consider the conformal transformation of this metric like the previous one. The uniformation problem goes as follows. So given a reference metric G hat AB, can one find a metric G AB with a constant negative Q curvature, lambda less than or equal to 0, that is conform equivalent to the GAB. So here you are supplementing a condition that our new metric GAB has to be a constant negative Q curvature. This is precisely the thing that we have seen in the two-dimensional case, because two-dimensional case your hyperbolic metric also has a constant curvature. So for that case, there is a precise action which is known for in even dimensions. I will not talk about any odd dimension in the case, because this Q curvature action doesn't make any sense in odd dimension. So let us stick to this even dimensional case. And in the even dimensional case, you can actually solve an analogous kind of equation, the Liouville equation, which goes as follows. So here there are this only holds for even dimensions, and there is some operators P of G. This is known as Graham-Jenne Mason-Sperling operator, and this QG is known as the Q curvature, which is in the reference metric. So all in the reference metric, and lambda is the Q curvature of your new metric GAB, that is basically negative. So you want to solve this equation. So let us see what this kind of operator looks like in 2 dimensions, 4 dimensions. Okay, so for 2-dimensional 4 dimensions, this operator looks like a so this is basically this operator is basically a generalization of Laplace operator. So in 2 dimensions, it's just a box operator. In 4 dimensions, this is a complicated operator which depends on the Ricci and Riemann of the particular background geometry. And the Q to the scalars basically R of R by 2, and Q4 is also a combination of Ricci and Ricci scalar and Ricci tensors. So the interesting to note that, okay, so for hyperbolic metric in 2 dimensions, you can, if you have a hyperbolic dz square plus dx square by over z square, you can directly check that if q2 is equal to -1 and q4 equals to -6. So one thing has to be noted that in 2 dimensions, for example, we'll see that in 2 dimensions, this q2 will appear, in 4 dimensions, q4 will appear. So in 2 dimensions, you see this constant, if you have a constant Ricci scalar, that automatically implies you have a constant q curvature. And also the opposite is also true. You have a constant q curvature, q2 is a constant r. But in 4 dimensions, if you have a constant Ricci, that automatically gives you a constant q curvature. But the opposite may not be true in general. The constant q4 doesn't imply the constant r in general. We should keep this in mind. Okay. So now you have a q curvature action. This action, you want to solve this action. So you find the equation of motion. This is the equation of motion where you have introduced an factor chi, which is the negative of this cosmological constant, because it is negative, this is positive. And now we take the reference metric as a flat metric. When you take the reference metric as a flat metric, this term goes away. We only have this term. So this is basically a very simple form. So del d of phi is phi over d phi. So with the supplement the boundary condition that minus tau is basically our z. So this condition 1 over epsilon square, we get a solution like this. This is the prefactor that we have. I have a prefactor that appears, and I have scaled as a mu. So mu is basically given by this factor. So this range of this factor. So the problem of the q curvature tells that your chi has to be from 0 to d minus 1 factor. This is the optimized metric in d dimensions. This automatically gives your mu has to be 0 from 0 to 1. And the optimization conditions that we have seen yesterday, that is given by this chi equals to d minus 1 factorial. So for example, in 2-dimensional, you can see this chi equals to 1 basically. This is precisely the q curvature is -1. This is known as the Gauss curvature in 2 dimensions. And the q curvature is basically the generalization of the Gauss curvature. So in other dimensions, so in 4-dimensional, you can see this is the lambda equal to -6. The precisely the q curvature of the optimized geometry that we have already seen previously, -6. Okay, -6. Okay, so now you see the so far is so good. So somehow q curvature is giving a good result. So for that is, I mean, telling maybe there's complexity action, high dimensional complexity action, q curvature action may be a good candidate of a high dimensional complexity action. So now you want to check if this satisfies with other constraint condition. So yesterday Pavel has talked about this optimized metric that this your R2 is basically R2 plus 2 mu is equal to 0. This you can see this from directly from the Liouville equation. You can see this constraint. So that means your R2 by 2 is a minus mu, and R2 by 2 is basically your Q2, and Q2 is basically, and for optimization condition, your Q is basically -1. So this is already we have seen. For higher dimensions, he also showed that you have a phenomenological generation of this Liouville action. So and from that action, you can calculate the Ricci scalar, and this is given by the Ricci scalar. Okay, so for example, you can check in 4 dimensions. 4 dimension, you can get R12, and if you precisely formulate, use this formula into your q curvature action, this will get you will get a q curvature -6 that you have already found. So what does it tell? It tells that we don't need to actually put any the phenomenological generation that we have done. We actually basically is true, and q curvature action is also a quite natural generation of this Liouville action in higher dimensions in the perspective of the complexity actions, and they are quite a good agreement in this result. And so the main takeaway message is that depending upon this event dimensions, the geometry, the constant negative q curvature corresponds to the optimal geometry. The optimization corresponds to mu equals to 1, and this optimal geometry, you have a constant negative q curvature. And the interesting thing is that we do not require to choose mu equals to a high by hand with this, so that this is our optimization condition. Instead, boundary geometry automatically picks up the optimal way of performing the path integration. So as long as you tell that, okay, so we want a boundary of optimal geometry as a negative constant negative q curvature, you always have to choose mu equals to 1. That's it. And in terms of the Q curvature action, complexity action is more natural than the phenomenological generalization proposed yesterday. So basically, here you are generalizing case by case for each dimension, say you want to fix, but the Q curvature is automatically a generalization comes from this complex Q curvature action, and all the constraint that the complexity, this optimization concept that you have seen is automatically satisfied. You don't need to put something by hand; it's automatically inbuilt. And again, you can solve the equation with the solution. If you plug that solution into the Q curvature action and solve the on-shell action, you will get a complexity for dimension v d minus 1 by epsilon. So this is a volume law scaling in d dimension, d minus 1 dimensions, and your phase factor by epsilon. Okay, so this is from the boundary side. So do you have any questions? Okay. Let's go to the gravity side. So gravity side, we have this geometry that you have seen yesterday. We have a region M, and this is the asymptotic boundary epsilon with the tau is a time, and we have also have a time goes from this way along the surface Q, which is defined by z equals f tau. This is also holds for LD d plus 1 dimensions. It's not only d dimension, also holds for d plus 1 dimensions. So this is our geometry. You want to evaluate an action in this region. So the region action is given by this. So this is the Einstein-Hilbert term, which is supplemented by a Gibbons-Hawking term, and we want to add a tension term. So this is basically a bulk term. This is a boundary term. So this is the d plus 1. It's the d, and this is also brain action, which is a d-dimensional action. We want to add a brain tension. And in 2 dimensions that we have seen yesterday, that if you add these 2 terms, you will get exactly the Liouville equation. But the main message from this is that you can directly relate to the optimized solution from this reveal potential to the tension. So this is pictorially shown in this picture. If you have a t equal to 0, you have a mu equals to 1. So this is your optimized solution. This t equal to 0 slide. If you have a t equal to d minus 1, this is mu equal to 0. This is the most unoptimized case. And in between, you have a partially optimized geometry because t runs from this factor to this factor. So the take-home message is that for t equal to 0 for all d, the optimization corresponds to t equal to 0 for all d. Whatever dimension you can choose, if mu equals to 1 always, if you put t equals to 0. So now you can ask the question, okay, so okay, we have a brain tension which only have a volume term. You see, this is only a volume term. So you can ask if we add some curvature terms in the brain, does this result also follow? So we're going to add some curvature terms on the brain. So let us add some curvature terms on the brain. So this is our first term, volume term. So kappa is basically the overall constant, this Newton constant and everything. And you are adding some constant, it's alpha r plus beta r a b and gamma r. So this is r square term and this is a linear term in r. So this is a curly r because this r is made up on this the metric from the brain. So this is a curly r. So now the optimization condition. So for simplicity, if we choose beta and gamma equal to 0, and you want to choose alpha not equal to 0, and you want to optimize this metric, you want to add the gravitational action with the brain action, and you do the optimization, and you will get an equation like this. If alpha equal to 0, you will get you will only get the equation that we have seen yesterday. But if we have alpha not equal to 0, we will add a second term depending on this which. So this is nothing but the trace condition or the Newman-Neumann boundary condition, which is supplemented by a Einstein tensor, and HI is the metric of this thing. Okay. And so now we look for the solution. We want to find a solution of this. So we look for the solution of the form, but b is some constant, and we get the condition something like this. If you have alpha equal to 0, that you have, if you don't have any curvature on the brain, you have the right hand side is 0, and you have precisely this condition. But if you have a alpha not equal to 0, if you have the brain, you see this optimization mu equals to 1 does not correspond to t equal to 0 as long as alpha not equal to 0. So in principle, this is the quadratic equation in mu, and you can find a solution depending upon this alpha. There is there's a relation between alpha and tau. It's the second order relation. So but you can consider an optimized metric for mu equals to 1. So mu equals to 1 doesn't give you t equal to 0. Rather, there's a relation between alpha and t. So you can choose your alpha at t minus 1, and you can add a brain action like this. This is your first term, and this is your second term. So alpha r. So you can add a term like this. So what this means that you can still add a term. You can still add a term like this in your brain action, in your gravity action, and still find the optimized solution m equals to 1 without t not equal to 0. So what this corresponds means that if you go back to the picture, this is t equal to 0 slice. This is the optimized slice. But now we have optimized something, some tilted in some between, because we have a non-zero t, and there is some angle you can also find. For example, if you plug some value of t, you can find which angle you can have the surface. So the main message is that this works for, so the optimization doesn't correspond to t equal to 0 always. Okay. So what happens in 2 dimensions? You see that for the in 2 dimensions, this action actually breaks down. This is divergent. So if you go back to the previous condition, in this condition, you see this, if you have a 2 dimensions, right hand side always vanishes, whatever this alpha is, 0 or 1. So in 2 dimensions, you always have this condition, this conditions, which is basically the previous condition, this condition, which corresponds to t equal to 0 is optimized slice. So in 2D, irrespective of alpha, the optimization corresponds to t equal to 0, whether you can add your brain action or not. But in D greater than 2 dimensions, we can add curvature term from the brain and still preserve the optimized condition. This is basically m equals to 1 condition. So our demand is that m equals to 1 condition is the optimized condition, that because we have given that we have got from the Q curvature part that m equals to 1 corresponds to action. Okay. Now we can see, okay, if we have adding more terms in the brain, if we add higher curvature terms in the brain, that is also follow. If you add higher curvature terms in the brain, now all the terms alpha, beta, gamma not equal to 0, the solution gives like this. So you see, this is precisely, there is a d-2 factor and there is a d-2 whole factor. That means in d dimensions, again, these items will also vanish and t equal to 0 is the optimized solutions. But is in other than 2 dimensions, you can solve these equations for optimized conditions m equals to 1, and this leads to some condition. From this equation, you can see there are many choices of between alpha, beta, and gamma to choose between. See, and they precisely, and you can solve this equation to get a alpha. You can write alpha, beta, and gamma in terms of the tension, and you can solve this equation. For example, one choice is the following: that you can choose your alpha as in terms of this that we have previously chosen, and your beta plus gamma equal to 0. You have to choose this factor, so you choose beta minus gamma and gamma equals 1. So you can add a term like this. You will get a term like this. This is the beta and gamma factor. Get a term like this. The thing is that you can again add a higher curvature term in your action, and you still preserve the optimized condition with t not equal to 0 even. Okay. So this is a condition. So the summary is that okay. So we have a higher dimensional complexity action as a Q curvature action, and we have seen this optimization condition justifies for the Q curvature action. The solution justifies the boundary condition is the hyperbolic geometry, and we also see that we don't need to put m equals to 1 by hand or something. We get the from the optimization conditions from the Q curvature geometry. This m equals to 1 automatically appears as an optimization conditions as a uniformization problem. And again, we don't need any phenomenological generalization to add some action. Q curvature action is a valid action in even dimensional at least. Odd dimensional action, I'm not sure because this Q curvature action fails in odd dimensions. Next, we saw that in higher curvature terms, we can add in the brain. We can add higher curvature terms in the brain, and we see this is 2-dimensional case is an exceptional case because 2-dimensional case is t equal to 0 size always corresponds to the optimized case. But in d greater than 2, this you have a different choice between different choice of alpha, beta, and gamma you can add depending upon how weight you give the exact factor of this curvature, and you can add the term, and you can still preserve this optimization condition with t not equal to 0. So, and the last thing that I haven't talked about is that understanding penalty factors from the gravity side. So there is an interesting question that how can you use understanding penalty factors from the gravity perspective. So we have some results of penalty factors in terms of the Q curvature action, because if you formulate your problem in terms of this Q curvature action, so your penalty factor, you can see their penalty factors automatically arises, and from this gravity side, this bulk tension, you can directly control how this penalty factor directly is related to this tension of this brain. So there is a nice interpretation we can give from the penalty factor from the gravity side at least as well, which is not present at this moment. So thank you.
Okay, thanks, Pratik, for the very nice talk. The floor is open for questions. Please go ahead, ask questions. We have a raised hand from Hugo. Please go ahead.
Actually, I was just clapping for the talk.
Okay, I'm sorry.
I don't have any questions. Thank you.
Sorry, my bad. Okay, please go ahead and ask the questions if you have. So if there are no questions right now, so Pratik, can I ask a question? Hello?
Yeah, sure.
So maybe I was not following it very closely, but can you just give me like one quick reason why this thing construction fails in even odd dimensions? Like,
Okay, so
is something
actually,
parity thing is related to parity or something?
so this is related to anomaly action actually. So anomaly doesn't hold in the odd dimensions. So there's no analog of Q curvature action in odd dimensions, and you cannot also define these operators in GGMS operator in odd dimensions because they are related to d by 2. So there is no meaning of this PG and PG in the odd dimensions. This directly linked to the anomaly actions. You can find anomaly for even dimensions from this equation.
I see.
Yeah, so it's interesting to ask the questions of what happens in the complexity action in odd dimensions, but there is some consensus that odd dimensions you can have a Riemann tensor, Ricci tensor in your which plays an equivalent role in the Q curvature. Ricci curvature is a similar role plays in the Q curvature in odd dimensions, but thing is not very clear. But the even dimensions, the Q curvature is the generalized Gaussian curvature, Gauss curvature.
So from the gravity side, is there any understanding of why in the odd dimension there is this?
No, so far gravity side, these things works for all d+1 dimensions.
So that is why I'm difficult for me to understand. Like from gravity side, I don't see this difficulty at all. Like
right. This is gravity side. This is holds for all dimensions.
Are there terms in gravitational action which are also dimension dependent, like some wild?
I think this action comes from basically you start from the write down the corresponding anomaly term, Euler anomaly, whatever term, and that those terms exist only for event dimension. Then you make the cutoff z e to the power phi x and expand it, and then you get this Q curvature term actually. Q curvature term. So
this cutoff you're putting it in the bulk. You're talking about bulk.
Yes, so but make that dilaton field. That is why you get this effective dilaton action in terms of this Q curvature. So they only exist in odd. In that sense, they only exist in the odd dimension. Okay. Because this anomaly exists only in event dimension, even boundary dimension, even boundary.
But I was asking, is there some analogous action which is just defined in odd bulk dimension?
Okay, so no, I'm not sure about this. It's basically because in bulk dimension you also you consider this Einstein.
These terms are universal. That I understand.
Yeah. No, I'm not sure about this. For the bulk, it works perfectly. For the boundary, there is certain issues about this even odd dimension. I agree.
Okay, anybody else has any questions? Let me check if there are any raised hands. No. Can you show your summary slide once again?
Sorry?
Can you please show your summary slide?
Summary, okay.
So these higher curvature terms on the brain, they are not extrinsic curvature terms. You're putting intrinsic
The higher, yes. There's the only R. Yes.
And you also have some Ks which come from extrinsic geometry, right?
Right.
So what is the reason they're not important or they don't play a role?
Well, the first of all, we want to try to see whether this action has some counter term action like term. But we found that this action, because in counter term there you have a special kind of terms, right? This alpha, beta, and gamma. So we want to see if this is actually the counter term action, if you have some or analogous counter term action in the brain. So that's why you just keep only the R and things and try to evaluate this thing. But it's not exactly the counter term action. If you see the coefficient is not exact, but you can have a tune this coefficient in manner.
Nice. Okay, let's thank Pratik once more, and in a couple of minutes the next talk will begin. Gabor, are you around?
Yeah, I was around.
No,
yeah, I'm here. Hi.
Oh, yeah.
Should I stop sharing it?
Yeah, if you want, you can stop sharing.
Hi.
Hi, how are you, man?
Good. How are you?
All right. So, do you want to try and see if your presentation shows up?
Yes. Desktop one. Okay, right. It's working, right?
Yeah, I can see your cursor and everything. Yeah.
Yeah, great. Yeah, cursor is important.
Yeah. Okay, I think we can start. Welcome Gabor Sarosi from CERN. He's going to talk about the volume of black hole interior at late times. Very interesting topic. Please go ahead, Gabor.
Yeah, so first, thank you so much for this invitation. It's been a very inspiring workshop so far. So I'm going to tell you about work that appeared recently with Luca Eliasio and Mark Mazei. Okay, so here's the plan for the talk. I will start with motivating a little bit the problem, and then I will go on to describe the framework in which we did this work, which is JT gravity, and its important connection to random matrix theory. So I will give a very small brief review of this. And then in the third part, I will describe the results, which is about the calculation of the volume and non-perturbative corrections to it in this theory. Okay, so here's the motivation. We want to understand why the interior of a black hole grows. So this is kind of a common motivation for a lot of the previous talks. So essentially, if we take an eternal black hole, let's say in AdS, the interior is kind of like an expanding cosmology. As we move up in time, there's more and more space here, as measured by various kind of quantities. So a particularly nice quantity that measures this is the volume of a maximal Cauchy slice at a given anchoring time that grows linearly with time at late times. So the main question that we're after is what is the microscopic origin in the CFT of this creation of space here? Okay, so in the context of AdS-CFT, we have a nice handle that we aim to use to understand this. We know that the eternal black hole is dual to the thermofield double state, and at later times to the time evolution of this state. So we're looking for some probe of this quantum state of the CFT that probes this growth. And there are various standard probes like correlation functions or entanglement entropy, and we know that these are not going to cut it for this problem. And the reason is that this is kind of a thermal state, and these simple probes reach their final value in a relatively short time. So in some time set by the temperature. While on the other hand, the volume keeps growing, and it is expected to grow for a very long time because it's a property of the background.
So in your figure, in your diagrams, T is running up both sides on the up.
Yes.
T is including upwards in
This one, right? Yeah.
Common time for the both boundaries, right? This T.
Yes. Sorry?
This T is both boundaries. It's running upwards. Right?
Yes. Yes. Yeah. Otherwise, it would be just the same state.
Right.
Okay. So as I said, perturbative corrections in G Newton are unlikely to terminate at the growth of this volume. It's a property of the background. So essentially, we're looking for a quantity that is not thermalizing for times that are non-perturbative, so large that are non-perturbative in G Newton. So there's a candidate proposed by Susskind and collaborators that I don't have to introduce too much in this workshop, which is a complexity of a state. So let me anyways give a very small review about what complexity is supposed to mean and what kind of properties we expect from it. So this is just some measure of hardness of preparing a state with some restricted set of operations. So you could think about considering qubits, k qubits, and you only allow yourself to act with 2 qubit gates, and you want to get to some reference state that is arbitrarily given. And you start from let's say all qubits being 0. So you need to apply lots of these gates in succession, and then you could quantify the complexity of getting this state as by counting the minimal number of gates that you need here to get to this target state. Okay. Yeah, see also the very nice view of this by Shira. Okay, so this definition is of course somewhat ambiguous. So, and we're not even talking about field theories here. And even in the case of qubits, you could have different choices of gate sets and so on. But what is also ambiguous is how you measure the size of the interiors. So we will be interested in more like universal robust properties of this hardness of preparing a state when we talk about complexity. So let me briefly review what kind of such universal aspects we are expecting from the complexity of state preparation, especially if our target state is the time-evolved version of some state. So what kind of complexity this time evolution introduces. So first of all, at early times, you can think about this time evolution operator itself as a kind of quantum circuit, as the one that you see here. So if you discretize time and you act with a kind of approximation to a small exponential like this in succession, then you can think about each of these terms in this power as kind of a layer of a gate here, simply because these Hamiltonians are typically integrals of local operators. So that's some layer then. And then the depth of this circuit is determined by essentially how much time you want to evolve. Okay, so this is one layer. This is integral of a local quantity. So the total number of gates, if you interpret this as a kind of quantum circuit is roughly the number of degrees of freedom in a single layer, which is captured by the entropy of the system times the depth of the circuit, which is proportional to the time. So you get some kind of linear growth times the number of degrees of freedom. Okay. So of course, this is not necessarily a minimal one, but suppose that this is the minimal one. So how long can this linear growth continue? It cannot continue forever because eventually you just run out of states in the Hilbert space, and you're guaranteed to get shortcuts to get to your target state. So when are we expecting to get to a shortcut? So here's a simple argument. We should look at, if we're looking at k qubits, this is the group of all possible unitary operations that you can look at k qubits, and we want to see how many of these are. So if you introduce some kind of tolerance, the number of possible unitaries must scale with the volume of this unitary group, which for large number of qubits is a doubly exponential scaling. So these are roughly like the total number of unitaries that you connect with on a k qubit. On the other hand, if you start to build a quantum circuit and you increase the depth, again, you will, at the given depth, you will have more and more possible quantum circuits. So what's the number of possible quantum circuits? It's the number of fundamental gates to the power of how many gates you have. And that's just the width of the circuit times the depth of the circuit. So this is something growing exponentially with k. So now you can see that if you put a circuit depth, which scales exponentially in k, the number of qubits, then essentially you have as many gates as many unitaries. So at this kind of depth, you expect that it's not worth to make the circuit longer because you can just prepare any kind of unitary with the circuit anyways. Because of this, the maximal complexity will scale in this way with the number of qubits. Supposing that the growth of complexity is linear in time, this leads to a saturation time that is exponential in the entropy. Okay, so this is the kind of cartoon picture for what kind of time dependence you expect for complexity in a chaotic system where this linear growth would be prolonged. So the picture is that you have this linear growth, and if it can last as long as a time required to reach maximal complexity, and once it reaches maximal complexity, it will just stay there. And then at very, very late times, you could have Poincare recurrences where complexity drops back again. Okay, so this is the rough picture. Okay, so when we want to map to AdS-CFT, then the expectation is that this linear growth maps to the growth of the black hole interior, this linear growth of the volume. So this is something that is described in semi-classical gravity. So the goal today, for today's talk, is to see whether we can see this saturation part where you reach maximal complexity in gravity. Okay. So before we move on, I just want to ask the question that you may ask, is that why do we even have a chance of seeing something like this in gravity? After all, this is an unperturbative effect that could require like a great control on stringy objects and so on. Okay, and the reason is because of recent developments that show that the Euclidean path integral in gravity seems to have an unreasonably large regime of validity, and it cannot capture such non-perturbative effects. So examples of this are universal energy level repulsion in chaotic systems. So this is about something about the discreteness of the spectrum. So it's, again, similarly non-perturbative. Or another such effect is the unitary page curve for an evaporating black hole. Okay, and the common thing about these two cases, how the Euclidean gravity path integral knows about these features, is via topology. So in the case of level repulsion, it's about wormholes, Euclidean wormholes connecting disconnected boundary conditions. While in the case of the page curve, it's similar wormholes, but connecting different replicas in the replica trick to calculate an entropy. Okay, so topologies are a key here. So today's goal is to see how do these topological effects affect the volume of the interior of black holes.
Gabor, is this a blanket statement, or is it like in very few contexts can you justify this Euclidean gravity applying so universally? For example, if I take a context in which, let's say, the BTZ, do I really see a thermal 2-point function, bouncing, or the Poincare recurrence part? Do I really see from some summing over topologies?
Well, Poincare recurrence you will not see for sure. But other very late time non-perturbative features, certain features of the two-point function you may see. So in 3 dimensions, we don't know really how to sum over all the topologies, but like one effect that you can see is contribution of some suppressed topologies, like wormholes connecting disconnected boundaries, leading to this so-called ramp. Let's say in a two-point function, and this has been analyzed in a set of papers that are not necessarily these, but connect to these. Other features are harder.
It is some intermediate state between the classical, the Heisenberg time and the Poincare. So that intermediate dynamic, some parts of it you expect to capture.
Yes, basically, yes. So the Poincare recurrence time would be something doubly exponential in the entropy of the system. And these are effects that are singly exponential in the entropy of the system. So it's already not classical, but not as late as Poincare recurrence.
Okay, thank you.
Just to comment, Shubhoda. So I think there are some papers by Damour and Solodukhin and Solodukhin who have considered, I think back in sometime early 2000s maybe, that if you have wormhole type structures, then if you sum over them, then you get this two-point function, some small fluctuations in the long time behavior of two-point functions.
Okay.
Yeah.
I didn't know about this. Okay, thank you. Okay.
Yeah, thanks. Okay, so this was the motivation. So now I will move on to describe Jackie-Teitel-bound gravity. So it's a simple 2D theory of gravity where you can actually do this sum over topologies. So in more realistic cases, we don't have enough control to really do this, but in such simple cases, we have. Okay, so this will be a kind of review. So this theory is, as I said, a two-dimensional theory, and it's not entirely trivial because it's a dilaton gravity theory, so it has an extra degree of freedom besides the metric, this phi. And this is the action. So there's a kind of Euler character term here. Sorry. This S0 is a parameter parameterizing kind of the ground state entropy. So this term is topological, and then this is the non-topological part of the action. So there's a bulk term, and then there's a boundary term, which is basically required for a well-defined variational principle and for holographic renormalization, because we're considering this. So this action has asymptotically AdS-II, nearly AdS-II solutions. Okay, so one important aspect of this action is that it arises as a dimensional reduction of near horizon geometry of many near extremal black holes. So it's kind of a universality class of near extremal black holes, a universality class of low energy dynamics of certain near extremal black holes. Okay, so how do black holes look like in this theory? So it does admit black hole solutions, and in Lorentzian, it's just global AdS-II. So it's like a strip like this. So how is it a black hole? In this theory, you put a cutoff at a large fixed constant value of the dilaton. So essentially, the dilaton profile tells you where's the boundary, the holographic screen, and I drew this in this solution. So this blue curve is where you put the boundary, and this is what makes this solution a black hole. So essentially, it has horizons. It's a two-sided eternal black hole, and inside this kind of Rindler patch, in the horizons, you can see that the metric looks like basically a Schwarzschild black hole. Okay, so when you consider this geometry in Euclidean, you just have the Poincare disk with a kind of uniform large radius cutoff. So it's a version of the cigar geometry in 2 dimensions. Okay, so these are classical black holes in this theory. So now we want to move on to the quantum theory. So how do we quantize this theory? And this is where the strength lies. So we want to do a path integral, and when we integrate over the dilaton variable, you can see that the dilaton only appears linearly in this action. So essentially, when you integrate out the dilaton along complex contour, then you just get a delta function that fixes the curvature. So since we're in 2 dimensions, this also just fixes basically the local geometry entirely. So all off-shell geometries are essentially pieces of hyperbolic space. So this enormously simplifies what kind of gravitational geometries you need to sum over. And this is what I will briefly describe now. So let's start with the case when the topology of space is just that of a disk. So that's the simplest example. So here's the hyperbolic disk, and then you pick some piece of the hyperbolic disk with a boundary condition that the boundary has a fixed length. So that's a thermal boundary condition. So it's set by the temperature. And then essentially the off-shell degrees of freedom of the theory are what is the shape that you cut out. So it's kind of a wiggly boundary. That is the off-shell degree of freedom. And it has a very nice action. It's coming from this boundary term, and it's described by Schwarzian derivative, basically of this profile of the cutout surface. Okay, so this is essentially the perturbative gravitational sector of this theory, and it's so simple that even at the quantum level, it's exactly solvable. So if you want to calculate the disk partition function, then you need to consider this action and integrate over all these cutout shapes, modeled out by some gauge group that defines equivalent contribution or equivalent configurations. And it turns out that this integral is one loop exact. So you can do it exactly, and it has this very simple form. So this has been shown by Stanford and Witten. Okay, so this is about the perturbative quantum theory here to all orders, but with a fixed topology. So now let us move on to describe adding topology to this. So if you want to kind of define the full quantum gravity theory want to calculate this full thermal partition function, then you would want to feel like sum over all the geometries that have fixed circle boundary of fixed length. So these higher topologies, there's also a topological term in the action, and that's what suppresses these higher topologies. They will be suppressed by this Euler character. So you have this kind of type of genus expansion, and we want to describe this, and this has been done by Saad, Schenker, and Stanford. So the way it works is that for the disk we have this one loop exact integral that I just showed you, and then we have a sum over genus, so for all surfaces, and then we have an expression that looks like this. So this is constructed by surgery. So we look at these surfaces, and we can always cut them into kind of a part containing the holes, kind of geodesic neck that separates that from the true boundary. So there will be a part of the path integral that doesn't have holes and goes between a wiggly boundary and the geodesic boundary. So this is again a kind of one loop exact integral, and it's like a trumpet partition function. So that's how we call it. It depends on the length of this boundary and the length of this geodesic. And again, it has a simple form once you do the one loop exact integral. And then the other part is a Riemann surface with one geodesic boundary, but different genus. So here, the path integral is essentially summing over all such surfaces with given local metric, which gives the moduli space, the volume of the moduli space of such surfaces, and that's what's written here. So this is the volume of moduli space of bordered Riemann surfaces. It depends again on this next size, and then the only variable that you haven't integrated over yet is the size of this neck. So that's why this explicitly integral is here. Okay, so this is the structure of the genus expansion. So this works very similarly for n boundaries. So in this case, you will get the moduli space of bordered Riemann surfaces with n geodesic boundaries. And then this kind of leads to a special UV completion of this theory. So this is kind of the logic. So these moduli space volumes, they satisfy a recursion relation found by Mirzakhani. And this recursion relation is related to the genus expansion in matrix integrals. So there's a recursion for matrix integrals as well. And this was noticed by Sarchenker and Stanford, who then used this to show that JT gravity is holographically dual to a matrix integral. So essentially, if you calculate the partition function in JT gravity with the thermal boundary condition, the way you should think about it is that it's a trace of it's quantum partition function, so trace of a Gibbs state averaged over Hamiltonians in a random matrix ensemble. Okay, so this squiggly equality means that, of course, this statement comes with various baggages. So the ones I want to highlight here is that this is true in the genus expansion, order by order. So this is but the right-hand side is non-perturbatively completed by the left, but the left-hand side is not. So the left-hand side is only defined in this genus expansion. That's one comment. And the other is that you need to take a double scaling limit in order for this to be true, which means that you take the size of these matrices to be infinite and you zoom to the bottom of the spectrum so that it remains discrete. Okay, so these are the comments here, and this is the duality that we will be using. Okay, so any questions at this point? Good. Yes.
Sorry, you can go ahead. There are no questions.
Yeah. Sorry. Okay. So now let me describe our results about the volume in JT gravity. So let me start by just quickly reviewing the classical volume. So I was showing you these Lorentzian black hole solutions in this theory. They are characterized by particular trajectory of constant dilaton surface, which is the boundary. And this is just global AdS. So now if you ask what is the volume of a maximal slice, it's just a straight line, and you need to just calculate the portion of the straight line that lies between these two blue curves. And of course also renormalize it, because when you send these blue curves really to the asymptotic boundary, you would get a divergence, but that's universal. And essentially what you get is a very simple formula like this. And what I want to highlight is that as for general black holes, when the time is much larger than the temperature scale, this is giving you a linear growth. Okay, so let's again proceed going ahead and define the quantum volume layer by layer. So first, let's focus on trivial topology on the disk, but let's take into account quantum corrections. So how would we define the quantum volume at this perturbative level? So the easiest way to define it in this case is using the Hartlocking wave function. So you can define a Hartlocking wave function for a thermophile double state by doing this kind of path integral. So the argument of the wave function is a length or a volume, and you do an integral with an asymptotic boundary of fixed length, beta over 2, and the geodesic boundary of length L. So again, this is a one loop exact integral. So the only reason I put here this Bessel function formula is that you see that while in generic gravity theories, this is an object you can't calculate exactly. Here in JT gravity, there's an exact formula that you can obtain. And it looks like this. So once you have this Hartlocking wave function, you calculate the quantum volume basically by taking the modulus square of the wave function and inserting the volume as a kind of operator in it and taking an expectation value with respect to the measure in which this is an orthonormal basis. Okay, so pictorially, it means that you take a cat and a bra of this Hartlocking state and you insert the volume here and do this integral. Okay, so this is a kind of perturbative definition. But now what we want to understand is a non-perturbative definition. And here there are more difficulties to overcome. So the main challenge is that once you include higher genus surfaces, then you have an infinite number of extremal geodesics going between 2 points. So how do you pick, what do you do? How do you pick from them? So just here, this figure is just meant to convince you that indeed there are infinite number of geodesics on higher genus surfaces. So for example, if you have genus 1, a boundary here, and you want geodesics between this point and this point, I have shown you 3. They are going in topologically different ways. And if you want to mathematically understand this, the way you do it is that you cut this surface open along the blue curve and the red curve. So this, once you do this, you can spread the surface out into pieces of a hyperbolic disk with identifications. And on this figure, the geodesics are just semicircles that are allowed to bounce. So for example, between these 2 points, you could have a direct one that corresponds to this orange one, or you could bounce to the blue surface and come back here, or you can do more complicated bounces like the green surface, and there's an infinite number of bounces that will take you from one point to the other. Okay, so what should we do then? How should we define the volumes? So one idea would be to take the minimal length one on each of these surfaces, but that's problematic because this is now a Euclidean picture I'm showing you because we're using the Euclidean path integral, but then we want to analytically continue these endpoints into Lorentzian values. And the minimal geodesic just jumps around if you change this value here. Like if you change the value of the endpoint, there are many transitions, so it's an analytic function of the endpoint. We would like to construct an analytic function of the endpoint that has a chance of continuing to late Lorentzian times. Okay, so we discard this option. And there's another thing that you can do. It's a kind of democratic thing. Is that, okay, so I'm just gonna sum over all the geodesics on a given surface. Okay, so this means that I do path integral over gravity, so wiggles and moduli space, sum over the surfaces, and for each genus I sum over all the possible geodesics. So this formula looks pretty sick because it's clearly divergent. Geodesics are longer and longer, and I'm summing over the length of them. So here I'm adding longer and longer numbers. So it's a huge divergence. But of course, we typically don't get too scared of divergences. We regularize them and try to understand them afterwards. So let's do that. So one natural regularization that you can do is that instead of summing over the lengths, you sum over e to the minus delta times the length. You can think about this delta as some sort of tension that you give to this surface. So this now something that looks convergent because you're adding smaller and smaller things. And once you have this, you can extract the quantity above by taking a derivative with respect to this data parameter and sending data to 0. Okay.
I'm sorry, can you repeat? How should I think about this delta as? You said something, I couldn't hear you clearly. How should I think about this delta as?
Yeah, you can think about it multiple ways, but one possible way to think about it is that you imagine that you're inserting a defect between 2 points with some tension, and then this delta is the tension of this defect. So in this sense, this is like a kind of Rényi entropy type quantity to the volume.
Okay, thank you.
Okay. At the same time, because we're in 2 dimensions, you can also recognize this as something that looks like a 2-point function. So if you have a 2-point function, it's also kind of, it's like e to the minus the conformal dimension or the mass of the bulk field times the geodesic length between the endpoints of the 2-point function. Okay. Yeah, so this is what I just said. So if I were to sum over all geodesics here, then this would be the 2-point function, the one that I used to regulate. But I will actually not sum over all geodesics here, just a subclass, well-defined subclass. So now I explain what subclass is this and why do I restrict there. Okay, so the subclass is a class of non-self-intersecting geodesics. So for example, here you can see a non-self-intersecting geodesics between 2 points, and here you can see a self-intersecting one between 2 points. So we ditch these and only keep these type of guys. And the kind of heuristic for this is that if you cut this geometry open here, then a state can live on this slice. So you can think about this as a contribution to the interior Cauchy slice, a wave function living on a possible interior Cauchy slice, while you cannot really do that in this case. So there's no Cauchy slice interpretation for an intersecting geodesic. So this is kind of inspired by this tensor network intuitions for the volume and complexity, but otherwise it's a choice. We also make this choice because this is the case where we can make good progress. So here's some other examples of the case of genus 2, what kind of non-self-intersecting geodesics you have. And then the main tool that we're using is kind of similar as in the disk case, that we cut open the path integral here and we insert the volume. And notice that if you cut this path integral open, you, instead of one boundaries, you will have two boundaries. So this is kind of the key feature here. So, and as I said, this gives you a kind of technical simplicity because you can just cut along these geodesics and insert this operator. So let me give you slightly more detail here.
Just a quick question, Gabor.
Yes,
hi, Gabor. Are these geodesics that you're summing over homologous to the, say, the lower half Euclidean path integral in the boundary of the manifold, or not? They're just not.
Not all of them. Yeah.
Not all of them. Okay, great. So even the ones that you're summing over, which are non-self-intersecting, some of them may not be homologous to the lower half space path integral.
Yeah, I think not. So I haven't thought about this question particular, but I think not. So they can just go over like under a handle, and then you cannot deform them.
Got it. Great, thank you.
Okay, so here's another figure explaining what kind of calculation we're doing, or what's the intuition behind it. So again, on the disk, we do a kind of integral over these possible value arguments of the wave function. There's an insertion, and there's the modulus square, and this is how we pictorially represent the modulus square. So this is replaced at higher genus by a similar formula, where you cut the boundary into two pieces along a geodesic, like this, and you insert this operator here, and then this is the kind of structure you have. So you have two trumpets, and behind that hides some two geodesic boundary Riemann surface, either connected or disconnected. Here I'm showing a connected contribution. So you need to understand this with surgery. And this is the kind of structure. So you have the moduli space that you would have for two boundaries, and you have two kind of trumpet wave functions that connect this to the asymptotic boundary and the geodesic. And then of course you have an integral over the geodesic line. Okay, so I should mention that you may notice that here there's no sum over geodesics, and the reason is that the real technical trick here is that how you eliminate this sum over geodesics. So it kind of turns the one boundary moduli space into the two boundary moduli space, and this is an important trick that has been used by Mirzakhani for deriving the recursion relation. Okay, so once you grind through this, you get a kind of formula that looks like this. So this is the result. So now the structure of this is not surprising. So there's in terms of the random matrix variables, there's a spectral two-point function appearing, and that's a two-boundary quantity. So the reason this two-boundary quantity appears is precisely because of this cutting procedure. And then there is a kernel here that comes from doing the integral over the geodesic length and the trumpet wave functions. It has some particular explicit form, and this is already not a two-point function, but the geodesic length. Okay, so you get this formula, and the important feature here is that we want to understand late times. So when you make the time large, It means that you focus on small energy differences. So actually this huge form here is not very important, but what's important is how it behaves when the energies are nearby, and it gives you a kind of singularity, which is quadratic, so like a double pole. And that's the most important feature of this expression, this kernel that you get here. Okay, so now you can actually evaluate this formula at late times, because now we are sensitive to small energy spacings, and in matrix integrals, this is universal. So the form of the spectral two-point function is that it has a kind of classical contribution, which is just product of spectral densities. So this comes from the disk topology in the path integral. There is a kind of contact term, so we will not be too worried about this. This gives you a divergence, if you can see it. So this is the kind of divergence that we were regulating. So it comes from summing over these longer and longer geodesics. And it's a divergence because there's a delta function, and here there's a singularity at the same place. But the important point here is that since the time couples to the energy difference, this divergence is time independent. So a finite quantity is the time derivative of this volume. There's no divergences in the time derivative. Okay, and now I arrive to the most important piece of this spectral two-point function, is this sine kernel form, universal sine kernel form. So there's two components here. There's a kind of power law decay, which is spectral repulsion, and it's controlled by the first kind of non-trivial topology with two boundaries, the double trumpet geometry. And then this sine piece here that regulates this when the energies actually lie on top of each other is a doubly non-perturbative effect. So this is where the non-perturbative completion of the theory as a matrix integral is important. Okay, so now you have this formula. Everything is explicit, so you can evaluate this integral and check how it looks like. And this is how it looks like. So here I have scaled out these extremal entropies, these large parameters suppressing the topology. So time is in units of e to the s, and also the length is in those units. And you get a curve like this. So you have, this is kind of, if you numerically integrate this, so you have a classical growing piece, or a linearly growing piece that matches the classical calculation. And then you have a saturation to a constant. And the saturation is a kind of, has a slow structure like this. Okay, so as a reminder, this is precisely what we expect from the behavior of complexity. So there's a linear growth, and at exponentially large times, it saturates at an exponentially large value. Okay, good. So this is the main result. And in closing, how do I do with time? Okay, I'm pretty good. So I want to make a few comments on this formula, because it raises various puzzles, and it also has some very nice features, like how this happens. So first I will explain how this happens, like what it relies on, how this saturation happens. So in order to understand this, it's good to look at a very similar quantity that is well understood, the spectral form factor. So the spectral form factor is a two boundary quantity, so two partition functions, and analytically continued in temperature. So this has been studied a lot, and it has a kind of famous type of behavior and a relation to the information problem. And it has a very similar formula in JT gravity or in random matrices in general to what we have found for the volume. So you have spectral two-point functions, some Boltzmann weights, some phases, and you have nothing, just one for this quantity, the spectral form factor, and for the volume you have this kernel that came from integrating the volume. So what differences this gives you? It tells you that both are controlled by at late times by this spectral density two-point function, but different features will lead to this saturation. So this is how the spectral form factor looks like. There's a classical region. It goes to a dip. There is a linear rise here too, and then it goes to a plateau. So the contribution of these disk topologies, these classical contributions, in the form factor gives you a decaying contribution. So it decays late times like power law. So very quickly at exponential times, it's basically exponentially small. But in the case of the volume, it's just the volume of the interior growth that you find classically. So it's a linearly growing forever contribution. On the other hand, this sine kernel contribution gives you this entire part of the curve for spectrum form factor. So it gives you the ramp. It also gives you a plateau. So this happens because of a cancellation between non-perturbative contributions inside this formula. While in the case of the volume, this extra singularity that you have from M turns this into something that's very small for a long time, and then it becomes a growing contribution, just a negative one. And the reason you have here a volume plateau is an exact cancellation between this classical contribution and the doubly non-perturbative contribution. So this is a kind of interesting aspect here. Okay. So another comment I want to make is about the noise on the volume plateau. So if you remember, for complexity, I was showing that okay, there can be some fluctuations around the plateau, but on the other hand, in the JT gravity plot, it just was a smooth curve. So why is this? So the reason is that JT gravity is dual to this random matrix integral, which is an ensemble. And I have calculated to you the one moment of the volume, basically the expectation value where the noise is averaged out. So in order for in this theory to quantify the size of the noise, we need to sort of calculate the square of the volume and the average of that. So the rules of the game in JT gravity is that you need for these two copies of basically the black hole, the Euclidean black hole geometry with the geodesics, and you must allow wormholes between, like, geometries that connect the two. So you will have kind of contributions like this. So there's two copies of the Euclidean or the thermal boundary condition, also the geodesic endpoints, and then you have all these kind of geodesics or geometries and pairs of geodesics in them. And as you can see, here, if you cut along both of the geodesics, then instead of a 4-boundary geometry, you will have instead of a 2-boundary geometry, sorry, you will have a 4-boundary geometry once you make the cut. So because of this, when you derive the random matrix dual to this expression, instead of spectra 2-point function, it will depend on spectra 4-point function. Okay, so once you do this, you will find the following with a couple of choices that you need to make that I will tell you more about. But the result that you find is that the variance of the volume, so the expectation value of the square of the difference, square root of that, grows like square root of t. And this is for all times that are very large compared to the entropy. So essentially, the picture is that the variance is not plateauing; it's growing forever. But because it's a square root growth, it remains much smaller than the signal itself, the volume, for a very long time, even on the plateau, and then it opens up. So basically, in this regime, where the time is order exponential in the entropy, signal to noise ratio is highly suppressed. While in the regime where time is exponential of 2 times the entropy, then signal to noise becomes order 1. So this is the weird feature that we find. So comments on this behavior is that for complexity you would not expect this at all. For complexity you would expect the noise to just not change on the plateau, and that actually you expect it to be order 1 size. The other comment is that the calculation that we have made suggests that the noise is highly non-Gaussian. So we just calculated the second moment, but it's a calculation that suggests that it's not something that is coming from weak contractions. And this is contrary to the spectrum form factor, which has a Gaussian noise. And the last and most important comment is that we have made a bunch of choices, and you can ask whether we are calculating the variance right. So one of the most important choices that we made is to not include pairs of geodesics between the two boundaries that intersect. So this is another choice compared to not including self-intersecting geodesics, because these are neither of them self-intersect, but they do intersect each other. There's technical reasons for this. So we essentially just examined one candidate for the variance. So let me summarize. So I have defined for you regularized non-perturbative volume in Jackie-Teitelbaum gravity. And I have showed that it saturates at exponentially large times in the entropy. And this is a behavior that is also expected from complexity. So the result that you get is very similar looking at what you get for the spectral form factor, but the origin of the ramp and the plateau are a bit different, because in the case of the form factor, it's a cancellation between non-perturbative contributions, while in the case of the volume, it's a cancellation between the classical and the non-perturbative contribution. Okay, so there are many open questions. So first, in order to really reach this volume plateau, I have needed the full sine kernel, which is a doubly non-perturbative object. So in fact, what I haven't told you is that if you truncate that sine kernel in a genus expansion, then at any finite order, it gives the wrong approximation to the curve. So then it's important to understand like what's the real geometric origin of this saturation. So we don't really have that. We made an all order expression. We completed it with the matrix integral. We have seen the saturation, but we don't see like where in the geometry really it is coming from. Okay, another important comment is that this is not actually just in JT gravity. This final formula that we had for the volume makes sense in any matrix integral, and we are not just extrapolating from one example, because it can also be derived in more general cases of 2D gravity when you have a general dilaton potential. So these cases, how these different dilaton potentials correspond to different random matrix ensembles were discussed in these papers. And for this class, this formula is the same. So you can kind of define a spectral complexity for random matrices that looks like this. It's actually, you can define it in any quantum system and ask whether it matches some definition of complexity or some universal behavior of complexity. So there's many problems with how this would work, but since we have basically derived that in these theories, this expression is what holographic complexity is, you must ask this question. Okay. So the other puzzle is that the late time variance is way larger than expected, and it's not equilibrating. So there are possible resolutions to this puzzle, but it should be understood better. And then, of course, you could ask whether there are lessons that you can draw in higher dimensions. For example, since we're in late times, you might expect that the spectral density 2-point function is still in control. So this deserves further study. Okay, so thank you very much for your attention.
Thanks, Gabor, very much for the very nice talk. The floor is open for questions now. Please go ahead. Onkar, go ahead.
Hi, Gabor, thanks for the nice talk. I just had a question about your spectral complexity. From this expression, is it possible to derive some formula for the time at which this linear growth starts to saturate? Is there some formula for the sort of the time at which it starts to saturate in terms of energy eigenvalues, for example?
Yeah, so it's a kind of a very slow saturation that you see. So this formula for so the saturation depends on statistics of nearby energy eigenvalues, which in chaotic systems is universal. So essentially, it's the same analysis that I was showing you, and you get this very slowly saturating curve where you scale out the number of eigenvalues. So that's what controls it, and there's no very sharp time because as you can see, it's like it's a slow saturation, but the curve is a scaling curve. So once you scale out the number of eigenvalues, it's a fixed curve.
I see. Well, the reason I was asking is because there are somewhat related formulas for the time at which complexity growth encounters, say, conjugate points, and these formulas often also depend on like spectral statistics. Essentially, nothing more. It's just these conjugate point locations depend on spectral statistics, and so one wonders whether somehow that is a possible in for how to sort of relate your spectral complexity to, say, Nielsen complexity or something like that. But sorry, this is a very speculative comment.
Yeah. So thanks a lot. It's very interesting.
Sure.
It's a good place to start.
Okay, are there any more questions? Please go ahead and ask. If nobody has questions, can I ask a question? Yeah. So a couple of slides back, can you go back a couple of slides when you were comparing the spectral form factor with the complexity, and you were mentioning that there are some large cancellations which lead to the plateau behavior in the complexity?
Yes. Here, this.
Here. So you had an explanation why you expect that plateau, because of the cancellation between the first term and the third term contribution, something like that. Am I correct?
Yeah. So that's the case. So this is a cancellation that happens in this formula. And it's
one of them is like, I can think of it is like a classical tree-level effect, and the other is non-perturbative in G Newton. Am I right?
Yes. Yeah.
Because I cannot see any G Newton, that's why I'm asking. Is there any way to see, or is it just the topology? That is what I should understand as.
So is there a way to see what? Sorry.
The G Newton, the fact that this is non-perturbative in quantum gravity, or non-perturbative effect in quantum gravity, because I don't
like
see the G Newton.
This fact. Okay. Yeah. So it's the fact that you have So each row 1-point function is something that's exponential in the entropy. So here you see that this is the largest contribution because we have 2 of these. And the entropy is 1/G Newton. So this is something e to the 2/G Newton. So this is suppressed already because you have only one factor here. So it's suppressed by 1 factor of e to the minus s. And then when you look at this thing here you have this one row here inside the sign, which is sum of 2 exponentials. So you have an e to the 1/G in the exponent, so it's like an e to the 1/G effect here.
Okay. Thank you.
There's so you should actually think about this sine square as kind of like a 1 minus cos, and then there's a 1 which has e to the minus 2s suppression, and it's like a wormhole contribution, and then there's something that is like AA instanton. Yeah.
Right. So from these 2 cancellation, you don't have time explicitly in this formula, but let me recycle Omkar's question. So if I were to find out some critical time where these 2 contributions would start canceling, is there a way I can set it up? I can extract some time in which such 2 contributions start to cancel.
Yeah, so what the cancellation means here essentially is that, so you see that time is here in this formula. So you go for nearby energies. So you take the limit when E1 is close to E2, and the cancellation is because, so there are various singularities here. So if you were left with a singularity, then there would be no cancellation, but there's a, so what happens is that when you start to expand this near E1 minus E2, it's not just the leading singularity that cancels, but the subleading one too. The cancellation of the leading singularity is the cancellation in the spectral form factor. So that's just when you look at this part of the formula, you see that naively it seems like it diverges here, but since the sign goes to 0, when this is small, like the leading double pole is is killed here, and then the formula is regular. But here, in our case, there is this M, and it gives you like another double pole that multiplies this. So this cancellation is not enough. You also need a cancellation in the subleading term of the expansion of this sign.
Right.
And the kind of magic is that that subleading term is the same as what you get from this factorized contribution.
Right. So so if E1 is not exactly E2, there'll be some time dependence, right? There'll be some linear. If I don't consider exactly E1 equals E2, then from E to the IET, there's some time dependence, right? Some linear.
Yes.
So I'm trying to see if by some quick back of the envelope calculation, you can get a value of T for which these two terms exactly cancel versus they're not.
Yeah, so the best thing I can say is essentially what we did in the paper, which is you can kind of scale out the entropy factors from all the variables and make the formula a scaling formula, and then you have a scaling curve that saturates at some order one number value of the scaling time that's measured in terms of the entropy. Maybe it can be made sharper in some limit of the temperature, though.
Maybe I should look at the paper.
There's a so I guess there's a sharper time in the micro. If you look at like a microcanonical version of this quantity, where you could say that here you have like a center of mass energy, total energy, and an energy difference, and when you just drop the center of mass energy integral, so that's like a microcanonical version of this quantity. There is going to be a sharp value for the saturation.
I see. Also, in the plot which you had, which was like a continuous, can we do what you had? Very nice picture of two tangents which were meeting at some particular time. The asymptotic tangents.
Yeah, so you could do something like that. Yeah, but these are just asymptotic expansions. But so you could define like the crossing point as a
Right.
time. But if you take one more order in the asymptotic expansion, it will move to some other time.
Oh, I see. Okay.
So maybe this microcanonical version, I think, is the best defined because there, like the curve is really like a piecewise curve in the microcanonical ensemble. So there's an approach to saturation and there's an actual constant. And,
right. Okay. Okay. Are there any more questions? Comments? So the next session is scheduled at 8 p.m. We have a 1 hour break because it is dinner time, time for dinner in India. In the meanwhile, the speakers are around. Pratik and Gabor, if you have any questions, please go ahead and ask. Pratik is around, right?
Yes, I am around.
Okay.
At least for half an hour.
Perhaps I can ask Gabor a more speculative question.
Yeah,
this is about the definition of complexity. So you decided to sort of sum over all possible geodesics which are non-self-intersecting. But do you have any comments about like potentially other choices? Like, for example, one thing that comes to mind is like one could imagine just summing over geodesics which are sort of homologous to the, say, lower half space path integral in the boundary. Somehow taking inspiration from the RT formula or something like that. So yeah, sorry, this is a very speculative question, but yeah, do you have any comments about other choices?
So we did examine a bunch of other choices, but not this particular one that you're mentioning. Yeah, I can tell you about a bit what kind of other choices we thought you could make, and what's the problem with them. So I have already explained why like taking the minimal length in Euclidean is not okay. But you could sort of have a proxy for the minimal one by let's say taking the log of the correlator and taking delta to be large. So instead of doing what we do when you take data in the correlator to be small, you could take it to be large, and you would expect this on each surface to kind of select like a minimal length.
Right.
Geodesic. But the problem with this is that then you have a large back reaction from this correlator, and for example, you spoil the linear growth for long times, because the one important difference between this thing that we find, this limit, is that it goes to zero limit, and the actual 2-point function is that for the actual 2-point function already the kind of Schwarzian contributions, they change the exponential decay of the correlator into a power law decay. And this would transition into kind of linear growth, and when quantum corrections, perturbative ones kick in, the linear growth slows down and becomes a logarithmic growth. And this is essentially because of back reaction. And when you take data to zero, then you remove this back reaction from probing the volume. Okay, so this is one particular other realization that you could imagine. This homology constraint that you say, we haven't thought about that.
Okay, great. Thank you so much. Yeah, thank you.
Okay, so anybody else have any questions?
I think can stop the recording and leave the Zoom open, and practically we meet like 8 p.m., like 1 hour from now.
Yeah, let's stop the recording then.
Here model, let's like a model at infinite temperature. Like we want to ask what's the size of operator. And basically, from number, it's a
Hi, Ying, you're breaking out a bit. Hello?
You are muted, actually.
You've muted.
okay. Now, can you hear me now?
Yeah, it was a bit choppy at the last few seconds. So I couldn't hear you. So.
Okay. So we started the size of about the size of the operator, and we talk about the size of operator as well. It's basically a fermion counting, and here's the exact definition from these papers by Robert, Stanford, and Stryker. If you stare at this definition, you see that it basically counts the average number of fermions in this operator, and at finite temperature, it's defined as by Xiaoliang Qi and Alex Stryker. It's defined as an infinite temperature of this operator subtract of the background. I mean, if you look at this definition, you see that what it means is basically you size out infinite temperature size of this operator acting on a thermal background. Then you subtract out the size of the operator in this background, then you do appropriate normalization, overall normalization. It's a well-known fact, let's review here, is that when you define size of operator this way, the thermal size of a single fermion, let's say psi1 is a single fermion, psi1 of t is a Heisenberg time evolved single fermion operator. This thermal size can be related to an out of time ordered 4-point function, which grows exponentially until it saturates to maximal at the time of order T star, where T star is scrambling time. Roughly speaking, this size, let's say 1 minus this size is what we call F4, is essentially a 4-point function. This is a known fact from earlier work. I mean, this work, we will generalize this fact. And another thing is that let's get some intuitive understanding about this 4-point function. If you look at the relation between the 4 points, you see that this is a 1 minus the size over maximal size. So the size of this operator, I mean, as we discussed before, in epidemic model, I mean, this size essentially is the size of epidemic. This size over maximal size is a probability of picking a gate. When you pick a gate, this is a probability that you pick a sick gate, and 1 minus this is a probability of a gate being healthy. This is just some intuitive understanding. I mean, if you get it, that's great. If you don't get it, don't worry too much about it. It will help our understanding, but it's not really essential. It's F4 it's just probability of a gate being healthy with 1 perturbation present. Let's come back to our case. We discussed the collision in the black hole interior. So in order to prepare such a state, one thing is clear is that we need 2 perturbations. There's 1 perturbation comes from left and 1 perturbation comes from right. So the operator that builds the circuit described above is like this. Let's say we start from thermal field double, roll to the 1/2. We apply a perturbation, then we do Lorentzian time evolution. We apply another perturbation, then we do certain amount of Lorentzian time evolution. And we want to detect so we have an operator like this. And we want to ask, is there a fault, is there a time fault in this circuit or not? In order to answer this question, what we do is that we define, again, the renormalized size of this guy by taking the infinite temperature size of this, subtract of the background, size of the background. When we say the background, we mean basically take the same thing and get rid of the 2 perturbations, just the size of this guy, subtract of size of this guy without the perturbations. Then we do some overall normalization. Before going to computation, let's just get some intuition why things like this work. Let's focus on numerator. See that when there is no time fault, what we have is size of this guy, subtract of size of this guy. Basically, it's the same thing, just with or without this perturbation. And when we do have a time fault, we have used size of this guy, subtract of size of this guy. And clear that when this subtract this, probably roughly speaking, you don't have much left. But when you have this subtract out this, the existence of this fault will make a non-trivial contribution to this difference. We'll make this more precise later, but this is the rough intuition that why something like this could detect the existence of a fault like this. So without the fault, the renormalized size does not grow. In the case when the sum of time is negative, the fault makes a non-trivial contribution to the renormalized size. And this contribution grows as the fault grows. Another thing is that earlier we said that the size of an operator with a single perturbation is actually related to an out of time ordered 4-point function. And in this case, we have a size of an operator with 2 perturbations. And if you play with it, you'll be able to see that it actually can be written as a 6-point correlation function, where again, this size is 1 minus F6, where F6 is a particular 6-point function. And it's actually, its bulk interpretation is rather simple about this 6-point function. This 6-point function is like, let's say we start from thermal field double, we send something from left, something from right, and then we prepare a state like this. But in the bracket, we have a state. Then we take a left-right correlator at large time AB. Then we do normalization, overall normalization here. So the bulk meaning is clear. Next, we want to we say that our logic is that we propose that the happening of collision is because of the overlap. This overlap means the fold in the circuit. Then we want to diagnose the existence of this fold in the circuit. How? We look at something called size, which is related to 6-point function. So clearly the next task is to do some actual calculation about this 6-point function. What we will do is that we will calculate this 6-point function in Schwarzian theory. This is a contour representation of the 6-point function. By the way, our this calculation mostly follows from this paper. And this paper did a calculation of 4-point function in Schwarzian. We generalized their calculation to 6-point function. And you see that you have 6 contours here. The rough idea is that we will compute a correlator by performing a path integral over time reparameterizations, T of U. T of U is time parameterizations, weighted by the Schwarzian action. And let's say here, so we have G of a delta. So this S is a Schwarzian action. We integrate over T of U is a time reparameterization. And this guy are by locals representing the coupling of an operator pair to the Schwarzian mode. And these are the times. We see that left time has an extra factor of minus I pi here. I mean, the detail doesn't really matter. If you are interested in the details, you can either look at our paper or look at original paper by Medicina Stanford and Yang. So the key assumption here is that, as we said, we will integrate over T of U, where T of U is a time reparameterization mode. The key assumption is here that we actually assume T of U has such form where is a piece like a SL2 transformation. And the SL2 transformation are parameterized by X plus Y, X minus, Y plus, Y minus. So, and here, so we start from a thermal saddle point solution. And then we, on top of this, we do some SL2 transformation. So this is a key assumption is of this form. So at the end of the day, the integral, the functional integral over T of U reduced to an ordinary integral over X plus, X minus, Y plus, Y minus. That's the key assumption used. Of course, the Schwarzian action also reduced to a function of just X plus, Y plus, X minus, Y minus. I won't go through the details. So the rough idea of calculation is as we discussed before, the functional integrals reduced to ordinary integral of 4 variables. Here's the result. Let's first look at a case with large positive A and B. With large positive A and B, the correlator is only a function of a sum of 2 times. And this is a happy result. This is exactly what we want. Because what we want is to diagnose that if the collision happens or not. And it should only be a function of the sum of this time. It should, because of the boost symmetry. And with large AB, exactly what happens is that correlator is only a function of the sum of this time. And here's the integral representation of this correlator with large AB. Roughly speaking, this P1 and P2 are the bulk momentum of the quanta created by the operator psi1 and psi2. And here's the correlator. And we can do this integral by saddle point approximation. And here is what we get. So far, I mean, all these calculations are calculations in Schwarzian. You can actually do a bulk calculation about you can do a bulk calculation about the same quantity. It's the correlator is basically the ratio of e to the minus delta, where this is a geodesic distance with the perturbation. This is a geodesic distance without the perturbation. You see that you actually get exactly the same answer with the saddle point approximation from Schwarzian, as long as you identify certain parameters. This delta S are the change of thermal entropy from the perturbation. This capital delta are the dimension of the operators. This is a certain amount of smearing. So let's say now we have the result of 6-point functions. What does it tell us about a collision? Let's say, why do we calculate a 6-point function? Because the 6-point function is related to size. What we're really interested in is the size, which is 1 minus f of 6. We see that when this guy is negative, then the size basically, roughly speaking, is just stays 0. And when this guy becomes positive, the size start to grow exponentially in this TWL plus minus of TWL plus TWR. And this is expected because for positive TWL plus TWR, there is no collision. That's why the size almost stays 0. So basically when there's no time fold, it's the size defined this way almost stays 0. And as we inject the perturbation earlier, when the sum of time becomes more negative, the size starts to grow exponentially in this sum of time. And this is consistent with the fact that the collision energy grows exponentially in this quantity. And there is a threshold here. When the sum of time is really large, how large? 2 scrambling time. The size saturates at its maximal value. And if you study the gravity solution, you will see that a large black hole has formed and the collision happens exponentially close to the singularity. So there is a transition happens at 2 scrambling time. Beyond 2 scrambling time, we actually have very little understanding about exactly what's happening in the black hole, in the bulk side. If you study the Penrose diagram, you will see that it happens exponentially close to the singularity. The details is no longer clear. All we can say that it's a fairly strong collision. Another thing is that we see that the transition happens at 2 scrambling time. I think all of us are very familiar with this kind of transition happening at 1 scrambling time. That's because we mostly studied the 4-point function. Now we study 6-point function, we see that there's a certain transition happening at 2 scrambling time. Okay, so this is basically the first part of a talk that we diagnose the happening of a collision. We know that if the collision happens or not, we know that how strong the collision is. We know that there is a transition at 2 scrambling time. The collision becomes super strong, and we can no longer say too much about the collision. The next task is that can we say describe this collision? Can we say more? Talk about more properties of the of this collision, and clearly that it's clear that in order to discuss more properties of this, we need to extract more properties of this quantum circuit. And as we said before, that the larger the overlap is, the stronger the collision is. Another thing we say that we look at is orange gates. Earlier we called them healthy gates, and we say that it can be undone from both sides. They are meaningless for one boundary system alone. And then let's look at this bulk geometry. These healthy gates clearly should be stored in the shared region. And this is in particular, these healthy gates, let's say in this overlap region, well, our proposal is that it's stored in this post-collision region. Later, we'll make a comparison with this not all the healthy gates. All the healthy gates here are stored in this entire entanglement region, but let's just focus on the healthy gates in this overlap region. And we want to compare this with the post-collision region. When we say that the healthy gates are stored in the post-collision region, so what do we mean by stored? We mean in the same sense of CV duality or CA duality, is that the growth of the number of these gates correspond to the growth of this region. In particular, we'll be able to see that in this case, actually, the the decrease of number of these gates corresponds to the shrink of this region. So if you are familiar with the geometry of a collision, you should be able to know that as we make the collision stronger and stronger, the post-collision region will first grow, then shrink. If you're not familiar with that, we'll review that later. But basically, it's just the number of healthy gates first increase, then decrease, and the region here first grow, then shrink. We'll review that later. So first, let's estimate the number of healthy gates in the overlap region. Actually, in order to estimate the number of healthy gates in the overlap region, we need to study another 6-point function, which is something like this, where we get rid of A and B. And one key feature is that this guy depends on 2 times, T1 and T2. Why do we study this quantity? Because, I mean, you probably don't have time here, but if you spend more time after the talk, you stare at it for longer time, you will see that from a point of view of an epidemic model, this guy is the probability of a gate being healthy with 2 perturbations present. So this is like some kind of size. This is the probability of being healthy with 2 perturbations present. And we first, we need to evaluate this guy. And recall that F4 is a probability, F4 is a 4-point function, 4-point OTOC. F4 is a probability of a gate being healthy with 1 perturbation present. So let's just follow our notes just from epidemic model. You want to ask what's the probability of a gate being healthy with 2 perturbation present. And we know the probability of a gate being healthy with 1 perturbation present. Then just follow our notes. This is the first order, this is 0th order estimate. You will see that this 6-point function will factorize into a product of a 4-point function. And indeed, we can actually evaluate this 6-point function with the same method before. I won't go through the detail, but it's exactly the same method. And we see that it does not exactly have this form, but approximately it factorizes. This kind of factorization was first pointed out in this paper. It's these authors wrote these 6-point functions as a product of 4-point functions with something they call the connected piece. And in this case, the connected piece stays very, very close to order 1. And here is the result. You don't need to pay too much attention to the details. And but one thing I want you to pay attention to is to understand the meaning of this F6 prime. Why do we need to compute this F6 prime? Recall that our goal is to estimate the total number of healthy gates in the overlap region. And F6 prime is, let's say, we fix a particular time. F6 prime is the probability of picking up healthy gates at a particular time. So the total number of healthy gates is the integral of this F6 prime. So a particular F6 prime is a probability of getting a healthy gates here. And when you do an integral with sum over all the healthy gates from the overlap region in the overlap region. Again, the detail doesn't really matter, but one thing I want to let you know is that just from the algebra, from the form of F6 prime, at the end of the day, the total number of healthy gates in this overlap region is only a function of delta t, is the only function of time difference here. It should be clear from the circuit picture that you see that the circuit has time translation symmetry. And indeed, when you carry out the algebra, you see that it's only a function of delta t, where delta t basically characterizes how strong the collision is. And we want to compare this feature to the growth of a post-collision region. So we need some quantity to characterize the post-collision region. Let's take a simplest quantity is a space-time volume. So why do I take space-time volume? Actually, just because space-time volume is easy to compute. Any reasonably defined quantity that characterizes the growth of this quantity, like a spatial volume, like action, geodesic distance, will basically behave, the time dependence will roughly behave in the same way. So let's say you have a signal from left, signal from right. What will happen in the post-collision region is that a larger black hole will form. And RH is the is the horizon radius before the collision. RH tilde is the horizon radius after the collision. And here's the relation between RH tilde and RH. You'll see that it starts to grow slowly, then it starts to grow significantly after 2 scrambling time. And so our goal is to estimate the space-time volume of the post-collision region. We did a calculation in BTZ black hole. And I won't go through the details here, but the only I want you to pay attention to is that it's a function of delta t, where delta t is minus TWL minus TWR. It will be very clear of the boost because of the boost symmetry of thermal field double. It's the size of this guy only depends on time difference delta t. So we have 2 quantities that both depends on delta t. The total number of healthy gates in the overlap region in the quantum circuit, where we computed through some integral of 6-point function, it only depends on delta t. And the space-time volume of post-collision region, where we just evaluated, also depends on delta t. And here is the comparison here. The blue line here is a volume, is a space-time volume. And the orange line here is the number of healthy gates. We see that they don't exactly match, but they are fairly close. In order to see this, we actually take the derivative of this guy with respect to delta t. And we see an exact match, except for at the very beginning and at around 2 scrambling time. And someone may ask that why do we get a linear growth and a linear increase and a linear decrease? It's actually fairly easy to understand. Let's say if you just draw some picture, and we see that the growth of a size is they first grow exponentially in time, then saturate. If you approximate this thing by step function, then you will get an exact linear growth and exact linear decrease. And then on top of this, you'll have some exponential corrections. And in this case, the exponential corrections in the middle, let's say between 1 scrambling time and 2 scrambling time, they actually also exactly match. So what matches here is the linear growth piece and the exponential corrections. The way they deviate in a way that say exactly how do you start from a transition from a 0 to this exponential growth, and how do you, so eventually at the end of the day you have an exponential decrease. The way they deviate in some transition regime, which I think is fairly important, but I have to admit that we also have very little understanding, but the bulk of the calculation, they agree fairly well. And I personally like this result very much because honestly, when I do the calculation, I didn't expect that they would have such good match. Somehow, before I did the calculation, I had the impression that the post-collision region is fairly messy. But now we clearly see that there's some clearly an important next step question, which we are exploring to understand this in more general context. Let's say one-sided collision, let's say localized collision, etc. So then here comes to the last part of the talk is so we know how to diagnose the happening of the collision. We know how to strong or not. We can even say something about collision. For example, we can estimate the space-time volume of the post-collision region. And then we want to ask, is it possible to extract the information about the collision? We ask more ambitious question. Is it possible to not only detect the collision from outside, but to extract the collision product from the wormhole? And the mechanism we'll do this is through traversable wormhole. So let's look at this picture. Here's a setup. Let's say from left side, we call it psi L. And this is a background. Psi L is the background. Right side, and then we do a traversable wormhole type coupling to get phi R out. I mean, ideally, in an ideal world, we would like to get both of signal out. But as we'll discuss later, from computations, you see that actually the best we can do is to get one of the signals out. But the signals will carry some memory about this collision. So the rough idea is that from traversable type coupling, we get this one of the signal out, we get right signal out, we get phi signal out, where the signal we get out here carries some memory about this collision. So roughly speaking, the setup is to get the expectation value from left side with the, let's say we have a background. The background is you send some signal from left, you send some signal from right, then you do the coupling here, then you get the expectation value of this thing from left side. So roughly speaking, we want to extract the signal that has the memory of the collision. So recall that epsilon R and epsilon L characterize the signal from left, epsilon R characterize the signal from right. So we want something that carries memory of both signals. So we need to look for the quantities that are proportional to this term, epsilon R, epsilon L square. And if you play with this a little bit, you'll see that it's actually something like this. I don't think in the talk you will have time to really digest this. But the point is just we basically closely follow. So the initial traversable wormhole paper, this famous paper is basically give the setup, and our calculation, again, it follows the calculation here. I mean, they did the traversable wormhole calculation without a collision, so it's a 4-point function. We basically generalize this to 6-point function. So effectively, at the end of the day, the statement is that what we need to do is we need to compute a certain 6-point function of the form. This 6-point function is not exactly the same as the 6-point function we computed before, but the similar method will apply. I mean, you first draw the contour, then you do the integral over the Schwarzian mode. At the end of the day, you get a fairly complicated thing, but let's try to understand this. Okay, so one thing I forgot to mention is that we say that we want to look for signals proportional to this, so we basically need this term. And this term is the imaginary part of a quantity called C. And so our goal is to understand when does the imaginary part of this C grows. We can first look at the probe limit. So do some approximation to this C. What approximation? Imagine we have some signal from left, something from right, and our goal is to get a signal from right side out. And in a first approximation, we can ignore the back reaction from the right signal. And here is what we have. It actually have a rather simple expression. And there is one feature about this expression is that this expression has a pole. In particular, okay, I didn't explain what are these times, but it doesn't really matter. So the fact that this C has a pole means that so there is a threshold. So beyond, so within certain range, there is no imaginary part. And then when you go beyond certain threshold, you get imaginary part. This existence of this pole is the first indication that a signal has exited the wormhole and reached the left boundary. And also, we can ask about the location of the pole. You'll see that the pole is basically it's a log of this thing and this thing. When this becomes negative, you'll get a pole. If you look at this, you'll see that there is a competition. There is a competition between the negative energy due to the teleportation operator and the positive energy due to the perturbation. If the one feature that doesn't exist in earlier traversable wormhole setup that appears here is that if the strength of the collision is too large, the ladder effect wins, the pole actually disappears and the signal does not exit the wormhole. So the pole is not always there. In order for the pole to be there, the the strength of the collision cannot be too strong. Let me go back to the picture and maybe we can see. So our goal is to get the right signal out. And the experience of this right signal is that it first collides with the green signal. Then it collides with the negative energy induced by this coupling. Then it comes out. So from the algebra, you will see that there's some computation between the strength of this collision and this collision. If the strength of this collision is too strong, the signal doesn't come out. And here is that probe limit. And here's the full computation result by numerics. The first panel is still in the probe limit. The lower panel is a full result from numerics. And this solid line basically is the imaginary part of the C. In this case, you see that it just has a pole at a certain point. And the three different panels basically is like we give the collision different strength. And we see that when the collision strength becomes too large, the signal disappears. In this case, again, we gradually increase the collision strength. And we see that as the collision becomes stronger and stronger, the signal becomes weaker and weaker, and it eventually goes away. So honestly, when we first saw this result, it's a little bit disappointing. So from one point of view, it's completely expected. On the other hand, it tells you that basically you can see only a very mild collision. The really interesting regime where the collision is strong, you won't be able to see that because that ruins the entire traversable wormhole setup. You can only see very mild collision. So how interesting is that? I mean, I don't know. I mean, of course, if you can do something in the lab, that would be great. But this is what we have. So at the very end, I will point out some unanswered questions. Throughout the talk, I've purposely avoided discussing one thing is the singularity. And actually, in this work, in this setup, this entire proposal, the existence of space-like singularity plays a crucial role. It prevents the meeting of signals that send in too late. But imagine if you have a charged black hole. Then if you trust the Penrose diagram, what will happen is that no matter how late you send in the signal, they will always be able to meet. And the meeting happens near the inner horizon. We have absolutely no understanding about that. In that case, why do they meet? And they meet, by the way, they meet in a regime where the dilettante value is negative. So what does that mean? Does that mean the gravity is repulsive? What does that mean? We just have absolutely no understanding. Recently, that regime was explored by these authors, and they said that there's something tricky about the physics near the inner horizon. It's just a very little explored regime. Another thing is that this entire picture of quantum circuit and the infalling object is only sensitive to the trajectory of the infalling object when it's close to the horizon. And so from the picture of the neutral black holes, one tends to say that at a singularity, the perturbation has smallest size and becomes simple. But again, this picture doesn't work for charged black holes, so we really shouldn't say anything conclusive about this. Another question is that how broadly does this meeting occur in general quantum systems? I think Sepehr later will talk about quantum gravity in the lab. And it looks like in that case, the traversable wormhole is a quite broad concept. And we expect the discussion of this meeting holds whenever the quantum system has a bulk due. But for more general quantum system, the meaning of meeting is not clear. But we expect it should be as general as the notion of ER equals EPR. So how general it is, can we make use of this? It's not clear. And another thing is more technical, is something we have been thinking about, is that I know that Jamie Sturdy also gave a talk on his work, is that if we want to use the growth of size to diagnose the interior property, then the question is how to incorporate the microstate information in the definition of a size. Because if you really want to talk about the interior, it should depend on the microstate and how to incorporate the microstate information in the definition. This is all I have. Thank you very much.
All right, thanks, Ying, for the very beautiful talk. The floor is open for questions now. People who have questions, please go ahead.
I have a question.
Yeah, please go
Is
ahead.
there any is there any effect of a spinning black hole on the information you can get from the collision?
Is there any information of what of the black hole?
No. Is there any effect of the spin of the black hole?
Spin of black hole, I don't know. It's the answer is I don't know, because we only did a calculation in the simplest case where is a neutral BTZ black hole. Spinning of the black hole is basically that will be a different background. Then the question will be twofold. One fold is that what's its effect on the quantum circuit? The second is that what's its effect on the collision in this background? That would be an interesting question where I never explored. Sorry, I don't know the answer.
Thank you, ma'am.
Ying, I have a question, just a curiosity about your comment at the end. You had you pointed out to this reference in the charged black hole case. Okay. You mentioned there something like it's tricky because the inner horizon we know has issues. So can you just summarize what is their conclusion? Like, is it like
you mean in this paper? Okay, I don't remember. I read this paper, but that was a while ago. Roughly speaking, I think they made some assumptions that, so there are, I think, 3 assumptions, something like that, where it looks like it's obviously true that, roughly speaking, is that the effective field theory still works, physics is still the same near the inner horizon. And after some computations, they draw a conclusion that those assumptions cannot hold simultaneously. Basically, they say that effective field theory needs to break down some way, but I really don't remember the details.
So there is some inconsistency in the assumptions you're saying. This is what the bottom line is.
Yeah, the bottom line is just the effective field theory may no longer holds near the inner horizon, but it's not conclusive. I mean, we discussed this. It's just a very little explore regime. I mean, this is one paper I know of that explore that regime, but overall we have very little understanding.
I see.
It's I find it very mysterious, that region. The fact that dilaton becomes negative, and what does that mean? Does it mean gravity is repulsive? So what does gravitational interaction look like in a regime like that? It's just yeah, we have very little understanding.
Okay. Anyone else has any questions?
Yeah, I have a quick question. So when you show the curve that is like the size that is growing and then decreasing, so what is precisely the time scale that when it start decrease? That is the scrambling time or no? Right?
Oh, okay, good. So you mean this plot?
Yeah. What is that peak?
So this time is a circuit time. You see that this time is 2 pi over beta times delta t.
I see.
So, and this horizontal line is proportional to delta t. And the post-collision region first grows, then decreases. And this is the first scrambling time. This is the second scrambling time. As we point out that there will be some transition happening at 2 scrambling time. So beyond 2 scrambling time, we have very little understanding. And the boundary quantity we look at becomes exponentially small. From the bulk side, the collision happens exponentially to the singularity. And we have very little understanding. So this is 1 scrambling time, 2 scrambling time. This panel is the time derivative of this panel. So almost 1, almost -1, then becomes exponentially small.
So when you say 2 scrambling time, I mean, these 2 scrambling times are not necessarily the same, right? It means first scrambling time or second scrambling time are the same magnitude wise, or?
What do you mean by magnitude wise? It's just the scrambling time is just a time interval. And there is certain transition happens at 2 scrambling time.
I think what we're trying to ask is it a different scrambling time? Like it's a different scrambling of a different kind of information.
Oh no, it's the same scrambling time as before.
Oh, I see.
It's the same scrambling time as the first defined by, I don't know, various authors, Lenny, Douglas, Stanford. But it's just in this case, the transition happens actually at 2 scrambling time because we are talking about the 6-point function.
Oh, I see. Oh,
And this is just a feature of, in particular, of the 6-point function, right? This you won't.
Yeah, it's a feature of a 6-point function that the transition happens at 2 scrambling time.
Okay. Yeah,
I
this
see.
new
So-
thing we had no idea. I mean,
Yeah,
so
when you evaluate
gravity-
this
from the
by
gravity
iconal
side,
method.
From
Sorry.
the gravity side, what is the understanding of this second scrambling time? This T2.
Okay, from gravity side, good question. That's what happens is this, is the strength of a collision is characterized by G Newton times S, where S is the collision energy square.
Okay.
And when G Newton S is of order 1, there will be so there will be new physics coming in, but we have very little understanding about.
So in the 4-point related thing is the 4-point function, we don't see the second scrambling time, right? We just
Yes,
see the
we don't
first-
see that. You need
first
6-point
one.
function to
I
see that.
So if, for example, do you think if you compute n OTOC, like keep on computing?
Yeah, probably
higher
you will
OTOC?
see more. You will see more. That's an
I see.
interesting direction. You just from point of computation of OTOC, I think it was pointed out initially by Dan Roberts and his friends. It's you will see more. And the gravity interpretation is not exactly clear. Here, there is for 6-point function, there is a clear gravity interpretation is that the collision becomes super strong and it happens very close to singularity. We already have very little understanding.
I saw an raise hand, right?
Yes.
So
Ma'am, if there's an observer within the black hole and it wants to and can it similarly gain information about a collision happening on the outside, if it's in a wormhole or black hole, something?
As far as I know of, the way to get collision product out is to do this kind of traversable wormhole thing. If someone stays in the interior, then well, he will see the collision and then he will die.
Okay.
Because the collision happens in the interior.
No, ma'am. I'm saying if someone is if the observer is inside the black hole,
Yeah.
and there's collision happening outside the event horizon,
then he won't see the collision. He won't see the collision because the collision happens is inside the horizon in the interior.
Okay, ma'am.
So let's see, the Penrose diagram is here. You see that, let's see, is there a better Penrose diagram? Yeah, the Penrose diagram is here. You'll see that this entire collision happens inside the horizon. So the tricky thing is that normally when we compute 4-point functions, let's say if you have a collision like this, then you can get some collision product out. And but in this case, the collision product fall towards the singularity. So you need to do something more complicated to get it out.
Thank you, ma'am.
So I just wanted to mention that there won't be any discussion section after the second talk of this session. You know, perhaps people, if you have questions, you can ask Ying right now. There won't be any other discussion section following this. Okay, if there are no other questions, then we can thank Ying for a very beautiful talk. We look forward to reading the paper. Very nice things in there, seems. Thank you very much for coming this early hour.
Thank you.
It's really early,
Thank
but
you.
we thank her this early. Okay, Sepehr Nezami is around, right? Sepehr is.
I think I need to stop share.
Yeah.
I'm making co-host.
Hello, hi, can you hear me?
Yeah.
we can hear you.
Also, I made you co-host, so you can try sharing.
Okay, can you see the screen now?
Yes.
Okay. So should I start?
Yeah, go ahead. Good morning to Sepehr Nezami from the West Coast. So he'll be talking about quantum gravity in the lab. Please go ahead.
And okay, thank you so much for inviting me and giving the opportunity to talk here. I'm going to talk about quantum gravity in the lab. which is based on these two papers with the archive numbers cited here. Joint work with Adam Brown, Frank Haripian, Stefan Leichenauer, Henry Lin, Grant Salton, Lenny Susskind, Brian Stringle, and Michael Walter. So it has a large amount in common with Ying's talk. So, but I will, since the talks are being recorded, I will somehow review most of the material. So it would be a standalone talk. So to start, let me talk about the motivation. But just before that, can I confirm that my sound is not echoing, because it's a problem that I sometimes have? Is it okay?
So far it's okay, I think. Yes.
Okay, thank you. So here our goal is basically, I'll start with the motivation, which is basically holography and noisy intermediate scale quantum error, which is called the NISQ era in quantum information community and quantum computation community. And basically the era when you don't have full-fledged fault-tolerant quantum computers, but you have devices with medium size and which are noisy. And we are planning to propose that quantum gravity experiments are particularly suited for this era, in particular if you have random looking Hamiltonian. So our goal is basically to explore the connections of quantum information theory and quantum gravity, but more importantly for the talk, design NISQ experiments for quantum gravity. And we want in this type of projects, we want to simulate the non-gravitational dual side of the holographic duality in the lab and detect the signatures of existence of the holographic dual in the lab. And so you can think about many different signatures of gravity. For example, you can look at Lyapunov exponents and other things, but here we choose a very natural signature, and that's the fact that things fall in gravity. And in particular, we are looking at the traversable wormhole space-time, and we want to observe that something that you release in this background geometry really falls as expected to fall in gravity. And the fact that you can receive an object that you release in gravitational background from one boundary to the other boundary is really a good signal of existence of a gravitational dual. So here is the rough picture. You have two boundaries and you release the particle and you receive it from the other side. But on the other hand, if you don't have this gravitational dual, it's really not expected to receive the signal from the other side. And so in this talk, I'm going to review a little bit of traversable wormhole, AdS-CFT, and dual quantum circuit. So that has a lot in common with the previous talks. I'm going to talk about state transfer and operator transfer protocols, different types of sending information in this geometric background. And then I will talk about an interesting fact that the same circuit that corresponds to traversable wormhole actually can send information in two different regimes. The first regime is the low capacity and high temperature regime that sends a little bit of information at very late times. And this type of teleportation is somehow unexpected from the gravitational picture. It's kind of unexpected from the Penrose diagrams that we draw. The second regime works at low temperatures and has a higher capacity, and that works near the scrambling time. And that is the kind of teleportation that is really dual to a particle falling in a traversable wormhole geometry. Then I will talk about size winding, which is a phenomenon that we propose as the dual of a traversable wormhole. And this is kind of a benchmark for detecting if your signal is actually going through a traversable wormhole, but not through the other regime that I just said is unexpected from gravity. And lastly, I'm going to quickly mention effects of noise and different approaches for preparing, measuring, and sending the signal in the lab, and end with the summary. So let me start with holographic duality. This audience, most of you are already very familiar with holographic duality. And so, but the basic idea is that certain complex quantum mechanical theories have a dual description in terms of theory of quantum gravity. So for example, if you have a cylinder here, you can put your conformal field theory or your complex quantum system on the boundary. And the dual picture is this whole quantum gravity that lives in the bulk, really inside the cylinder. And in particular, we are looking at something called the wormhole geometry, which has this type of Penrose diagram. This Penrose diagram has two boundaries, which I have marked with thick red lines, left line, the left line and the right line. And so this is a non-gravitational part. In most cases, in our cases, we assume that this is really the non-gravitational dual is really 2 points that are extended in time. So the vertical direction is time. And the gravitational dual is really the sheet of space-time connecting these two boundaries. The time in this picture goes from -infinity to +infinity on the both sides. And there's actually if you're familiar with Penrose diagram, this is really the laws of drawing a Penrose diagram that allows you to really compress this infinite space-time to a small sheet of paper, or this compact part of the screen. So you have to really compress everything such that the t equals -infinity and until to t plus infinity, the line from t -infinity to t plus infinity really is presented on this finite piece of line. So this is your boundary and this is the bulk. And the main thing that we preserve in Penrose diagrams is the direction of light. So the light travels at 45-degree angles, and things that go slower than light travel with an angle less than 45-degree angle. And what is the connection? So this picture doesn't look like a wormhole, but if I want to just quickly mention the connection to the actual wormhole geometry is that if this is a Penrose diagram for example, a higher dimensional space-time, we would assume that every point in this diagram is really, for example, a higher dimensional object, for example, a circle or a sphere, which is suppressed and presented by points. So this line from left to right is really nothing but, when you expand it, when you assume that each point is really a circle, is nothing but this double trumpet, these two trumpets, which form a wormhole. And if you go higher in time and you look at these different time slices, they correspond to longer and longer wormholes. The outside part, so this part of the line corresponds to the outside, the right black hole, and the inside, this piece of line corresponds to the cylinder, which corresponds to the interior of the wormhole, and the same for the left side. So this is really a picture of a wormhole growing and growing in time. But as I said, in this type, for simplicity of experiments, we are not assuming that you have higher dimensional objects, and we assume that the boundary is really a zero-dimensional object extended in time. And so it's a 0 + 1 dimensional object, and bulk is 1 + 1 dimensional. And to be more explicit, you have two boundaries, and the Hilbert space is the tensor paradox of these Hilbert spaces, and you have a Hamiltonian on the left and a Hamiltonian on the right, and the total Hamiltonian sum of these two Hamiltonians on the boundary system. An important fact is that the Hamiltonian on the left is assumed to be the transpose of Hamiltonian on the right. And the boundary state at time equal to 0 is the thermal field double state, which has some temperature. There's temperature that I'm talking before. And this state is nothing but a purification of a thermal state. On the bulk side, the connections is the dual is this sheet of space and connecting these two boundaries. And if you look at this picture, normally, if you release a particle on the lower left, it will go away to the singularity. So there is really no way that it can reach to the other boundary because it requires faster than light signaling. As you can see that the slope of the line should be less than 45-degree angles. It's This is imposed by the shape of this Penrose diagram. And on the boundary side, it's kind of clear that you will not be able to send a signal from left to right from quantum mechanical point of view. And that's because you cannot really send information without connection, without talking. These two guys, the guy sitting on the left, cannot send anything to the guy sitting on the right without really talking, implementing some gates or something like that, even in the presence of prior entanglement between them. So you really have to do something. If you don't do that, it's not possible to send information. So these two ways are consistent. But Gao, Jeffries, and Wall, as Ying nicely explained, propose a way to really make these wormholes traversable. And that is by making some kind of a interesting but weak connection between left and right boundaries, for example, at time equal to 0. And this coupling is a constant g divided by n is the number of qubits, z left, z right on different qubits. So you activate the first qubit on the left and first qubit on the right, and it has contributes to one of these terms, and you do apply the same ZZ coupling on all individual qubits. And if you do that, these people showed, and Gao, Jeffries, and Wall, and Muller, Smith, Stanford, and Yang showed that this would have an effect of sending a negative energy shock wave in the bulk, which essentially changes the geometry such that the particle that's free falling from lower left travels and goes back and be released and be received from in the right boundary. So you can actually send and transmit information from one boundary to the other boundary. And a nice fact about this coupling is that because there's a ZZ coupling, everything commutes. It can be converted to a genuine quantum teleportation protocol. So you can make measurements on the left-hand side, use entanglement existing in the thermal field double, and implement send classical information, implement some conditional operation on the right boundary to receive the signal. So it can be really transformed to a teleportation protocol. Yeah, and that's why I use the word teleportation, but sometimes I use the word teleportation even when we don't really make classical measurements, we just apply the coupling. And so this is a very fun fact. It just makes this nice geometry that you can really observe particles falling from the boundary point of view. At this point, hello?
Can I ask a question?
Yes, please.
Yeah, in this slide, in this Maldacena paper, they have the coupling as general operators OO, but is there a reason that you choose only ZZ for this 0 plus 1D model?
Yes, so you can use actually basically any operator. I use ZZ because it's the simplest operator. In addition, the fact that all the Z operators commute, all the operators that you have are nice operators with plus minus one eigenvalues, and they commute, allows you to easily convert this coupling to a classical teleportation protocol. For example, if you had ZZ and XX on the same site, which would work for making the wormhole traversable, you would not be able to convert that type of coupling to a genuine teleportation.
Okay, thanks.
So that's partly aesthetics, partly making a closer connection to teleportation. So now let me actually in detail explain what is the connection between this wormhole, what is the circuit wall of this picture and what is the circuit that we are going to implement in the lab. So as I said, we are looking at the boundaries. The left boundary is presented by the left-hand side of the circuit. So these two lines, a thick line, which contains most of the qubit, and a narrow line are comprising are making up the left boundary. And the same here, the thick line and the narrow line are making the right boundary. The narrow line in the circuit, the thin line of the circuit really representing the qubits where you put the signal on, and the thick line represents the most of the qubits where you don't put the signal, but you have the Hamiltonian acting there. And then you have to insert your signal by some kind of operation. I'll keep it general for now. It's E, the quantum operation that is acting on the message qubit at some negative time. So you have to sandwich it with some time evolution. And you have this ZZ coupling that's acting on all qubits but the message qubits. So this is really to make sure that you are not sending the information by acting the coupling directly on the message qubits. You want to make sure that this is being done in a holographic way. And at time, and you receive the signal by time evolving forward, and we're going to the time that you expected to receive the signal. So, and you put the signal here in the circuit and you receive it in psi out, and that would be the circuit corresponding to this teleportation protocol. And now the question is that how the circuit teleports. So from a quantum information point of view, this is kind of surprising that, or I would say unexpected, that this circuit can be used to send any information. Because if you look at this thing, you insert a signal here, you let it evolve, and after some time evolution, the signal is fully scrambled. There is really, it seems like the signal is lost. And then you act by some very mild coupling on left and right. Look at this, each individual ZZ term on the left and right side is suppressed by 1/n. So you really mildly touch individual qubits in the circuit on a scrambled data, and the time evolve it forward even further. So naively, as a quantum information theorist, I would be really surprised to see that any signal that is put here is coming out as in the psi out part. And this is kind of the magic of gravity, and that's what makes this circuit very interesting. We see that this circuit actually works, as I explained, in two regimes, one unexpected from gravity and one expected from gravity and through the wormhole. So if there is no other question, I will go through these two different regimes and explain them in the rest of the talk.
Hi, if I understand correctly, you're saying that the fact that the signal permeates through, despite the drop in the strength, is because of gravity, and there's no intrinsic boundary understanding of this?
No, I will present boundary understanding of both regimes.
Okay.
So, but I'm just saying that naively, this is a kind of a very interesting information theoretic task. So this is kind of what I want to communicate is some kind of a magic that is in gravity part is quite natural that the signal is falling. From quantum information point of view, what you see is a signal that is inserted in the circuit. It's fully lost through scrambling, is highly mixed with this chaotic time evolution. And then you touch it lightly, and then you evolve it further, and somehow reappears. And naively, it is surprising, but the part of this work is really explaining what happens on the boundary side, both in the regime that corresponds to a wormhole and in the regime that does not correspond to a clear geometric wormhole. So as I said, this circuit can teleport in two regimes. The first regime only requires scrambling dynamics, and it's kind of similar to many scrambling experiments that have been modeling quantum gravity. Oh, sorry, black holes. And it works best at the time scales when TL is very large and is equal to TR, which is very large. So the times, very late times. And it works best for very high temperatures. And this is the regime that the thermofield double is really nothing but the collection of bell pairs. At infinite temperature, thermofield double turns to bell pairs. And here we consider the insertion of the signal by this simple operation that you really trace out this qubit. You erase this qubit, the message qubit, and replace it by a fresh new qubit in state psi in. So you reset your qubit and place it in psi in, and you time evolve it, and you expect to get back the state that you inserted, psi in and psi out. And you can see that even for chaotic Hamiltonian, for chaotic non-holographic Hamiltonians, for example, when you put random numbers in individual matrix elements of your Hamiltonian, you can get a perfect signal out after the scrambling time. So this is the exact analytic results, that you put one qubit here, you start at time equal to 0 with no time evolution, the qubit just is really lost. But the moment you start time evolving, you can see that somehow the magic of the circuit works in a way that you get the signal back as a psi out. And this type of teleportation channel, interestingly enough, can teleport only one qubit. You cannot even send a Q3 with this type of, in the first regime at the very late time. So it is a very low capacity fine feature that requires scrambling. I will explain a bit later how this thing works. But let me, before going into the details, let me explain when the circuit works. As I said before, it works when you have any type of chaotic time evolution. For example, even if your time evolution is explained by a random unitary U, the circuit can send one qubit. And if your time evolution is something that you more close to experiments, for example, something like a spin chain, the circuit can send qubits. And in fact, if you have a spin chain in relatively early times, spin chain looks like many random blocks of unitaries in parallel. So with spin chains at relatively early time, you can send even more than one qubit. But when you wait enough, for a very long time, then the whole spin chain is mixing enough that it looks like a single random unitary block, and then you reduce the capacity to send only one qubit. So it works in different regimes, and we studied, for example, Brownian circuits, and it also works there. So you can send one, or sometimes in early times, even more than one qubit in the first regime. And the way to understand it is, I'm not going to explain the details, but the basic idea is that you can use some approximations and use some circuit equalities, and you can rewrite the circuit that you have here in terms of an equivalent circuit. I'm not going to talk about the details of this transportation. It's just like some few lines of algebra. It's not really crucial, but the basic idea is that the moment you have scrambling dynamics, the net effect of this coupling and this time evolutions would be implementing a channel that gives a phase to only one state in this double Hilbert space. And that state is a term of a double, infinite temperature term of a double. So the net effect of this, the whole coupling, the whole operations would be keeping everything but the thermophile double state the same, and giving a phase e to the ig to the single TFT maximally entangled state. And you can see that giving a phase to one state in the Hilbert space is powerful enough to send only one qubit, but this operation is not really powerful enough to send more than one qubit. It's a very fine thing to do. So this type of teleportation based on scrambling can send very little information, for most cases one qubit, and in some cases when you have a spin chain, more than one qubit at earlier times. And I will quickly go through the experimental requirement for this type of setup. So this is kind of a holography inspired teleportation. This is since the analysis also, so in this case, its first regime is has certain characteristics that make not only the analysis easier because it only relies on scrambling, it also makes the experimental realizations much easier because The starting state is a set of bell pairs and not TFT. And that is something easier to implement in the current lab, so people know how to implement bell pairs. The next thing that you have to do to run the circuit is forward and backward time evolution. And then you have to implement this weak left-right coupling, and again, time evolution forward, and you have to make measurements. So this type of experiment is something that can be realized in very near-term devices. And here you can see some simulations when you have a small number of qubits. So, so here is assuming, here we are making simulations assuming that your time evolution is the time evolution of something called a kicked quantumizing model. And here I assume that you have only 7 qubits on the left and 7 qubits on the right. And even after a small number of time steps, you can see a clear signal in the numerics, which are the dots, which is perfectly matching the analytical results. And here the case is, the point is that you can actually see this, all these observations, even with 7 qubits. And for the holographic case, for the genuine traversal wormhole, you probably need around 100 qubits. So this is a much simpler case. Teleports with the same circuit is holographically inspired, but it also can be performing near term, can be experimentally realized much sooner than the actual holographic case. And I'm not going to talk about that in the interest of time, but you can also see that this kind of circuit have some pleasant form of noise resilience for the near-term experiments. The reason is that, for example, if you have an error happening right before the coupling or near the time that you're going to implement the coupling, because the coupling really lightly touches individual qubits, the error will not propagate from left-hand side to the right-hand side, because even if you destroy one qubit doesn't matter that much because it's just going to be touched by a very weak coupling. So the circuit naturally has some nice form of resilience to decoherence noises in certain parts of the circuit. And we are currently working to see how we can improve this kind of resilience and use quantum recursion and other techniques to make this type of experiments feasible in to improve the signal and do an error mitigation, making it proposing a very strong experiment for this circuit. So is there any question?
Yes. I was thinking that it's this whole circuit diagram is motivated from holography, but in this example that you showed previously, if one does such teleportation, is there any gain over the conventional quantum teleportation just from the quantum computing point of view? If we forget holography and just think about the lab-based system, do we gain something by doing such circuit for quantum teleportation?
This is a very good question. And I'm not sure if, so this type of circuit the circuit naturally looks like some kind of quantum recursion circuit, because you encode your information in a very dispersed way and you send this very dispersed. So with this time evolution, you really spread the information. And so individual qubits don't matter. So it looks like a quantum encoding, but in general, if you are planning to be smarter and just use different techniques or use a little bit of fault tolerant ideas, I think you can easily beat this kind of circuit. So this is natural. It's a natural type of teleportation if you have a non-universal quantum computer, if you can just really implement some time evolution and simple couplings. But in the normal paradigm that people are thinking about teleportation, when you have access to different gates and you can easily implement Z or X gates, and it can do quantum error correction, I think you would find ways to beat this. So it's kind of, it's a very good question, but it kind of depends on the setup and tool and basically experimental tools that you have access to, what kind of gates that you can implement.
So would it be too simple to think that since you're using scrambling, like backward, after the message insertion, you're also doing some scrambling? Can one think that you're kind of making the information more secure because it's kind of now spread all throughout the system? Secure from stealing?
So I think this is exactly what I wanted to say. You do that, okay. And that makes your information secure, and that is why basically what I was saying that near the coupling you have very good noise resilience, exactly for the reason that you explained, because information is spread here, and if you mess up something here, it will not really destroy the information. The reason I was saying that this is not necessarily a kind of an optimal circuit for doing that is that because if you find an error maybe here or right after insertion of the signal or near the insertion of signal or near the point that you receive the signal, they would have been catastrophic. So in some places of the circuit, when you have the information nicely spread, that you're absolutely right, and there you have something that looks like a quantum error correcting code that can preserve, that can protect your signal because it's scrambled and it's spread.
Okay, thanks.
Thank you. So now I'm going to the second regime where we have a genuine holographic picture. But to do that, I have to have a quick detour and talk about the operator size a little bit. That's required for understanding how this traversable signal traversing through the wormhole works from the boundary point of view. So let me quickly explain the operator size distribution. So the normal operator size distribution is defined as follows. You have your operator O of t. You start with some small operator O, maybe living on 1 qubit. You time evolve it by some Hamiltonian, and then you expand it in the multi-qubit Pauli basis. So the CP coefficients are, you have 4 to the n of them, and these p's are Paulis. And the size of each Pauli is basically the number of x, y, or z operators appearing in its expansion. And we know that the operator size grows with time. As you increase the time, so here I'm plotting the CP coefficient. So this is the imaginary part of CP. This is the real part of the CP. And this is the operator size. For each size, you have many, many coefficients, and they are being plotted in this scatter plot. So at time equal to 0, most of the support of the operator is on a small qubits, on small size operators, when the size is small. And then when you increase the time, the operator grows, and you have support on larger and larger Pauli operators. And as you see that because this operator is Hermitian, or if this Hermitian, all these coefficients are real, so you don't see any imaginary part on CP. But for the traversal wormhole story, we have to actually look at a different type of operator called the thermal operator, which is defined as follows. You have this O of t that I had in the previous page, but I multiply it by rho beta to the power of 1/2. And now I expand this operator in this in the Pauli basis. I still have some CP coefficients, but now the CP coefficients can be complex, because on the right hand side you have the product of two Hermitian operators, O of t and rho beta to the power of 1/2. But the product of two Hermitian operators is famously non-Hermitian. So this operator can have complex coefficients. And I will explain how it's related to wormholes, but this is an ansatz that we have, we call size winding. And that is basically saying that as you increase the temperature, as you decrease the temperature, increase beta, and you're going from the picture of the previous slide to the current slide, this coefficient, the CP coefficients acquire a kind of a coherent phase. And they start obtaining a phase which is linear in the operator size. So you see here in this plot, and as you increase beta, the size distribution starts winding coherently. And it's kind of a surprising fact that, for example, you can analytically observe in the SYK model using the result of Zhao, and Alex's Stryker, and using an extension of the results of Zhao, and Alex's Stryker. And this is not a phenomenon that I usually expect to see for generic operators. So for example, if you look at the random Hamiltonians with no holographic dual, you see that as you increase the temperature, the CP coefficients don't stay on the line for each slice, but they just get going to something like an ellipse or a circle. So they don't coherently wind, they just get flattened and lose somehow the coherence. But the expectation that we have is that for systems with nice holographic dual, the systems where the traversable wormhole work, you have this particular phenomenon of size winding happening in the size distribution. And now I will go back to the wormhole picture and explain how it's related to the traversable wormhole. So I start with this picture that we have, and I insert a sig operator on the lower left. I insert a signal by acting an operator on the lower left of the traverse of the wormhole geometry. And you can look at this operator, the state of the system at time equal to 0, that would be a state on 2 Hilbert spaces. But we know that anytime that you have a state on 2 Hilberts and the tensor product of the Hilbert space times itself, you can actually rearrange the data in your state in an operator on one copy of the Hilbert space. This is called vectorizing and converting the vector to an operator. So basically what you do is that you look at all individual elements of the vector and put them as matrix elements of an operator. So we have here at time equal to 0, the operator corresponding to the state at time equal to 0 is nothing but O of t times rho beta to the power of 1/2. And the goal here is to receive the operator inserted on the lower left and the upper right. So after the action of the traversable wormhole, we expect to get an operator or transpose back on the upper right. So this would mean that the signal has traveled from lower left to the upper right. And interestingly, if you do a little bit of math, you will see that the operator corresponding to this state on the right is nothing but rho beta to the power of 1/2 times OT. So the order of OT and rho beta has changed when you go from the input state to the output state. And these two operators are Hermitian conjugates of each other. So now assume that you have an operator, if you assume that you have size winding, and you look at the size distribution of this operator on the lower left, and it would be something like some clockwise winding operator. And when you insert an operator on the upper right, because it's a Hermitian conjugate of this operator, all this CP coefficient, all of this, the whole size distribution would be complex conjugated. So now it would correspond to an operator that's winding counterclockwise. So somehow the goal of the whole traversable wormhole coupling is to convert this clockwise coupling winding operator to a counterclockwise winding operator. And this is what the coupling does. And you can see that the role of the coupling in general is to effectively add a linear phase proportional to G and operator size to individual CP coefficients. So the coupling just really turns any size, takes any size distribution that you have and starts winding it. And in this picture, what it does is that it takes this operator that has a clockwise winding, the coupling, as it has a linear phase, unwinds this size distribution and winds it to the opposite direction. In this way, it maps this operator that's clockwise winding to an operator that's counterclockwise winding. And this way, it maps OT times rho beta to the power of 1/2 to rho beta to the power of 1/2 times OT. And when you look at the vectorized version, vectorized picture, it maps the operator instead on lower left to the upper right. So this is the boundary mechanism of traversable wormholes. I wait here for questions. Is there any question here?
Sir, does Hawking radiation on any of the black holes cause any form of noise?
Sorry.
Does Hawking radiation on either the left or the right black hole cause any kind of noise?
Any kind of any kind of
noise in the signal.
Oh, well, I think the string effect would definitely create some noise. I don't think, well, I might be wrong, but I don't think the Hawking, because when you talk about this kind of eternal wormholes, you already have an equilibrium between Hawking radiation and the black hole. So I think the system is fully in equilibrium when you have eternal field double and a wormhole. I think if you go slightly out of equilibrium, that would manifest itself as some Hawking radiation and just probably introducing some noise. And but the exact way that the noise is introduced when you go slightly out of equilibrium and the effect of Hawking radiation in that is a very interesting question. It's something that we have been thinking, but I don't know a good answer for that. This is somehow in the picture of it somehow fits in the picture of wormhole tomography and what Ying was talking about, but I don't have better answers. But I think if you are in an ideal situation when you have an eternal wormhole, that should not create noise, I think.
Okay, thank you, sir.
Thank you. I might be wrong. So I will just say a few words about this size winding and size momentum correspondence. So it has been proposed that the momentum of a particle in the bulk is really dual to the size distribution of the boundary. And particle paper, Model Senna, Henry Lean, and Ying, they propose that the derivative of the size distribution is really explained, and the boundary is really dual to the momentum. But this size winding picture adds a new ingredient to the momentum wave function, to the size wave function, and that's a phase. So now we have a size distribution that is not only behaving like the momentum in terms of its absolute value, it also has a phase. So it really looks like a momentum wave function. And we can see that the rate that the size distribution winds is really, so in general, the rate that the momentum wave function winds determines the position of a particle. The speed of winding a momentum wave function is equal to the position of the particle. And you can see that if you analyze, for example, the S5K model here, the rate that the size distribution winds is equal to the distance of the particle from the black hole horizon. So the nice picture is that now you can have a very toy rough model of holography and emergence with space-time from the boundary point of view. And the toy model works as follows. You look at the size distribution. You start with a zero-dimensional object, which is a point with many degrees of freedom. And you look at the size distribution. The size distribution has a phase, and it does have a so it has a phase and it has just some width. There's a one-dimensional wave function, and you can directly interpret that as a one-dimensional wave function of a particle falling in the ball. So this really gives you a very raw holographic tool that ends up being sufficient for understanding the traverse of a wormhole story. And the nice fact is that even random non-local Hamiltonians demonstrate some weak form of size winding. So although they are not doing a perfect size winding, although these phases in the coefficients of the Pauli operators are not coherent, are not really nicely linear and coherent, you would have some weaker form of size winding that shares some physics of traverse of a wormhole, although it lacks a nice geometric picture. So, and this is something that you can hope to see in experiments in near term before you being able to actually run an experiment on the SYK model. So some signatures of gravity, some weak forms of size winding would be observable in more near-term experiments. And lastly, I would like to talk about some potential approaches for measuring traverse of a wormhole signal in quantum computers, and some of, again, ongoing research, so I would not be as precise here. And the main technique here is we wish to look for the size winding, and we want to make sure that if we see a teleportation, this teleportation occurs because of a winding size distribution, in order to make sure we are not confusing it with the first regime, which is non-holographic. And so there are different ways to see that. One of them is to really running the traverse of a wormhole circuit. The circuit I was talking about, you can run it in an experiment, but that may not be necessarily ideal because you need two n qubits on the left, n qubit on the right, and you have to prepare the term of the double state, which might be harder. There are other ideas that we are going through. One of them is using this quantum tomography techniques or shadow tomography techniques, or something called classical shadows. When you only look at this operator rho beta to the power of 1/2 times OT, and you make enough measurements on the state that is sufficient to infer the size distribution, and you indirectly measure the traverse of a wormhole signal. And in this kind of questions, we have in this line of research, we are also looking at how much, for example, quantum memory, a limited quantum memory, can help streamlining the measurements of traversable wormholes. And with that, I will end with some open problems. So one question is that beside the SYK model, what are the other interesting systems that we can what are the other models that can implemented in the near term? In particular, we are interested in finding models that we don't know if they have a clear holographic dual. So we want to propose experiments that test if this model has a holographic dual, and for that we are looking for different models that are not necessarily ruled out to be holographic, and that are not necessarily known to be holographic and not necessarily ruled out to be non-holographic, for example, for through the existence of unpleasant things like spin glasses. And the next question is that size winding in strong form exists in the gravitational systems, but in weak form exists even in GUE Hamiltonians. With GUE Hamiltonian, I mean Hamiltonians when you have random matrix elements. And the question is, are weak forms of size winding related to holography? Can we interpret this non-coherent size winding as something holographic? And lastly, we need a better non-gravitational understanding of the size winding. And my very last question is to construct tomography classical shadow protocols, which are really tailored to detect size winding and not using the off-the-shelf techniques, because they require exponentially many measurements, which could be prohibiting if you have more than 30 qubits. With that, I would end my talk, and thank you for your attention.
Thank you, Sepehr, for a very nice talk. The floor is open for questions. Please go ahead if you have questions.
So I have a maybe naive question that about this new technique. So the tomography or the classical shadow protocol for kind of setting a benchmark to test the gravity model in the lab. But all of this is kind of based on having a conformal large N model in the lab. Is that like the step 0 requirement, or can we surpass that in some way?
Well, so that is basically my first question here. For example, when you have a SYK model, you expect to see signals. You expect to see signatures of gravity, maybe with 60, 70 Majoranas. And with the sparse models of SYK, you can probably implement them easier. But the only problem with SYK is that you need really, in order to efficiently implement them, you need to have Majoranas, and you don't have Majorana fermions in the lab. So what you have to do is that you have to probably use you use certain mappings from Majorana to qubits. That would introduce some overhead and external locality that really makes everything much harder. So something that we are searching for is kind of models which are closer to experiments than large N conformal field theories, but will have some holographic signatures like this SYK.
Okay.
I mean, the example is SYK, and I think people expect for other. I don't think that I don't think that you need to have real large and conformal features to see signatures of things that have some form of gravity dual. Probably can find it in easier models. Some random matrix models, probably.
Okay.
I mean, large N limit, strictly speaking, large N gives you the classical limit of gravity. So classical gravitational phenomena. So if you keep N finite, your bulk will be extremely quantum, like heavily quantum.
Right.
So I mean, only if you want to see very classical gravity effect, GR effects, only then you need very large number of degrees of freedom.
Yes, so this is actually a good point, because one of the things that we propose to learning from this kind of experiments. So I think the really ideal case is that you have some unknown model that you can check if it does teleport. But I think that even if you have the SYK models or other things, in a small holography is one of the regions that more or less maybe 6 to 7 relatively small number of qubits is interesting, because it can give you the string corrections. When you go to very large N, and if you go to a GR limit, it's better understood. It's somehow like similar to thermodynamics, but not. Thermodynamics is easier maybe and solvable in just like billions of qubits, but it gets more interesting and harder if you go to maybe, sorry, not qubits, particles. But thermodynamics gets interesting and harder to control when you have, say, 70 or 80 particles. It's kind of the same here when you go to smaller n, you will see more significant string effects, which are extremely hard to compute analytically.
Yeah, I mean, in presence of those stringy effects, then this size momentum correspondence and this corresponds with the size winding and all that probably is not, I don't know, do you understand it yet? Or so these significant, so there are, yeah.
Yeah, yes. So this is related to something like Ying was talking about. Then you have, well, in general, model-sneer Stanford Yang also talked about, which is in the problem is when you have everything nice, so you have a really sharp peak for your signal. At some value, the traversal wormhole signal has a pole and it's very sharp and you get a perfect signal. But when you add extrinsic corrections, you see that this peak starts to, this pole, it starts to fade and you have some increased signal, and you remove the pole or you just weaken the power of the pole. So we know that stringy corrections will reduce the signal to some form, to some extent.
Okay, are there any other questions? So if there are no other questions, then we can thank the speaker, Sepehr, Nezami, once again. Thanks for a very nice talk and coming so early in the morning.
Thank you so much for inviting.
With that, we would like to conclude the session for today. Tomorrow, Arpan, do you want to talk about tomorrow's sessions?
No, so okay, so we thanks again all the speakers and we start at same time tomorrow.
Bartek, and we'll start with Bartek and
Onkar.
Onkar, right. So see you guys tomorrow at 3 p.m. Indian time. And once again, thanks very much.